as a supercompute center, want to provide to the scientists machine learning infrastructure. So they did purchase from NVIDIA a deep learning system, nice system, which has virtualization support for the GPUs. It has 8 GPU compute cards with proprietary high-performance interconnects. This diagram shows the architecture of these interconnects. How would a scientist use it? So there is an online calendar. You can do some reservations. You can book up to 6 hours, and kind of hopefully you're happy. Now, kind of as scientists rather are used to work hard close to the deadline, and then are not happy if the next 6-hour slot is maybe a week away. The next trend would be take some money available to the research group and purchase your own hardware. So in our building, a couple of research groups do machine learning based approach. We have a local department IT unit that operates it. So kind of in this enclosing, several racks full of hardware dedicated for machine learning number crunching is installed. And so the scientists kind of know, based on the budget they have, how to administer their resources themselves. Again, this is kind of overall costly and labor intensive to set it up. So hyperscaler companies come to the field and offer machine learning services. One example would be Amazon Web Services deep learning approach called DLAMI. Comes pre-installed, it gives pre-installed images with all the software scientists today like to apply. Amazon is not the only one with such offerings. Microsoft and Google and kind of a long tail of additional operators do this. So this would bring me to the statement: the machine learning infrastructure and having the software available, it's a commodity nowadays. So the question would be, is there something more important for machine learning applied to network systems than implementing the machine learning part? And that would bring me to my thesis, and please challenge me, or if you have other opinion. So I would say the big challenge is not the machine learning implementation, but having the right data. Of course, this asks about kind of what means right data. From my viewpoint, it means high quality data, and that will lead to high quality machine learning based solutions. Now, for the paper Fabien will present in this afternoon, kind of the assessment of his work was, well, much more time spent on dealing with the data than on the machine learning part itself. And our assumption is this is not a specific for our case. This is generally the case. If you work on a domain-specific problem, you need to have a good understanding on your domain-specific data, and then to produce the right data is hard, and to post-process it and so on. So this kind of why we need high-quality data, is it new? I would say no. I want to go back to past SIGCOMMs. So 15 years ago, together with 2 colleagues, I had initiated a workshop on models, methods, and tools for reproducible network research, abbreviated MOMA tools. Kind of a number of scientists gave presentations kind of more or less agreeing that the state of reproducibility in our domain, networking, is not very satisfactory. Everybody agreed we should be better. Everybody assumed, well, now they had some tools developed, and by probably applying them, issues should be solved soon. Well, the estimations were a bit too optimistic. So last year there was another workshop that still kind of identified there are big issues in insufficient or unsatisfactory reproducibility in our research domain. So despite all these 15 years of progress, most issues are still the same. Kind of, which are the right methods for reproducible computer network experiments? Kind of a need to discuss the different approaches and improvements presented by some. A need for commonly accepted tools and data sets in order to achieve the goal of reproducible research in computer networks. So I hope my talk will also inspire us to continue in this discussion and really make progress now. Among the problems to be addressed would be really identifying the root causes of what influences the performance of network systems, what to observe, which key performance indicators, how to measure them, how to build experiment setups for measuring them, and how to do the measurements in a replicable or even reproducible manner. Now, what's the meaning of these two words? ACM kind of explained repeatability, which is already not always the case. Like this graph in the paper was produced by a PhD candidate with a setup he even himself is not able to replicate a couple of, or repeat the experiment in a couple of weeks later. So repeatability would mean same people using the same setup and successfully repeat the results. Replicability would mean we kind of enable others to replicate our results by providing the relevant artifacts, scripts, data, documentation. So any other team should be able to replicate the results. And reproducibility would go again one step further, because kind of, what if there are some flaws in the scripts? So real reproducibility would mean we just explain in all relevant details what needs to be done to obtain the same insights without using our possibly flawed artifacts. Okay, now that the goal is set, when we talk about kind of data we want to achieve from experiments, how to assess their quality, I suggest looking at the following dimensions. Kind of, there would be precision, accuracy. I will quickly explain why this is not the same. You have a question?
You want questions now or here?
Now, please.
So, from an academic point of view, looking at doing user experiment and want people to be able to reproduce it, but looking at it from a commercial point of view, or a production point of view. Thank you. So, from an academic point of view, reproducing results is really important. You wrote a paper. I want to know, does it make sense? But from a commercial or production point of view, it's more interesting that you can actually get good results. You can predict something more accurately, or you can do something with the data that you couldn't do before. So you have a lot of emphasis on reproducing and these definitions. Do you also focus on how do I get high quality data so I can identify whatever I'm looking for in the network more accurately as opposed to being able to repeat it? Okay, good. Because there's a... Okay, thank you.
Okay, I suggested to apply different dimensions when talking about data quality, kind of apart from precision and accuracy. I want to introduce coverage and scope. Coverage in the sense, kind of, we measure a system which is possibly complex. Did we have it in all relevant states? And scope in the sense of, is the observation just of local significance because of our local environment? Or can we globally say this is what matters? Now first, let's come to precision and accuracy. Kind of precision would address kind of, are there random errors in the data generation process? Like, for example, in the traffic generator, if we configure it to produce data of a specified rate, would individual inter-packet gaps deviate from that configured value? And with which distribution? Accuracy, sometimes, for example, in ISO terminology, also called trueness, would look, is there a bias? Is there a systematic error in the observed data? So how close, in the case of our traffic generator, would the observed data rate be from the configured one? So this diagram here would show increased kind of trueness versus increased precision. So ideally, our observed data would be exactly where the red dot is, which is the ground truth. Maybe they are kind of spread away, both in some randomness, but also with a bias. Or maybe the randomness is reduced, but we still have the same bias. Or maybe we get rid of the bias, but we still have the randomness. And hopefully we manage to do our experiments such that we're here. And of course, this is not specific to our domain. This applies to all scientific domains. And my assessment would be computer network research was rather sloppy in looking at that. And the quality we apply, quality expectation we apply to even our high quality papers like in SIGCOMM is not where it should be. Or not always, let's phrase it this way. Okay, I had introduced more dimensions of quality. So coverage, I coined it this way because I was lacking kind of some other better word, would mean in which way do we cover average cases, and does our data set also contain the rare cases which may be relevant for describing in which states the system can be? And maybe some states are rare, but they are the cases where it really hurts, where it causes performance anomalies or some trouble, which cause the reason why we are investigating the whole thing. And so the challenge would be, are all relevant system states sufficiently covered in the observed data? Here I give one example of observing end-to-end delay, wherein kind of typical setups we would observe delays. So here the x-axis would be end-to-end delay. This would be probability density function. So in many cases we stay here, observe that, but there are some rare events with worse end-to-end delay. Somewhere is the actual worst case for a certain system with certain configuration and environmental conditions. But do we know it? Or do we have methods to estimate it? And here we can kind of easily see if our training data set for our machine learning method just contains this part, the outcome will fail if we are interested in kind of something that also may happen. Then to the next dimension I had talked about, scope of data. So we may have a local setup, our own configuration software that operates in that environment, some local users and usage patterns, maybe our own anomalies caused by some funny configuration. And if we evaluate that, what's the kind of significance of our results? Are the results of global significance? What can others learn from? So I would say we should aim for a global scope, kind of focusing on properties applicable to the systems where a wide range of systems have those properties in common, which would mean, for example, the hardware architecture, the software, starting from the operating system and the full stack of additional software on top of it, and the specific protocol stack with its configurations. And I want to suggest we should assess the data concerning in which way does it represent the global situation of the internet. Kind of, is it specific to all servers of this type? So how do we describe the type? And if we look at anomalies, are the anomalies representative? We should be aware kind of a lot of artifacts we look at is human caused. Some administrators configure in a not optimal way, but there are common mistakes. So hopefully they are in our data set. This leads me to kind of state the following vision. We should aim being able to analyze networked systems such that we can always understand the root causes of performance issues, do the right design decisions, and dimension appropriately. My statement here would be normally kind of, we can model in an explicit manner, but complexity is such that in real-world systems, kind of, we don't achieve our goals. So this is our hope that somehow in the collected data, the truth is there and machine learning methods allow us to do so. And with my vision, I would say we should then be able to dimension scalable systems, do so in an instrumented manner, that they constantly continue to deliver right data, which allows us to better understand how they are used and fix issues before they kind of really cause damage, or identify first and then fix. And have in these scalable systems the right algorithms that ensure scalability, the ability for intelligent analysis and adapting the systems where needed. And being able to master the complexity, all relevant complexity. And there I would suggest to look in the following dimensions: complexity of the protocol stack, of the hardware architectures, the software architectures, and where we add programmability, understanding this complexity too. So this would mean we need to kind of get a control on this complexity. And we face a trend towards increasing complexity, which kind of keeps us busy. And whenever we achieve something, kind of we still didn't reach the goal because the world outside of us added complexity. So which complexity do I talk of? So one dimension is protocol stack complexity. We were used kind of an explanation of the IP protocol stack as an hourglass with a kind of a waste of very limited complexity in the middle, IP protocol. In reality, it looks a bit more ugly. Kind of people in IETF constantly add stuff which makes some mechanisms being executed at some places where we may not expect this effect to happen, which makes it hard to interpret why is something not how we expect it to be. But this is not the only cause of complexity. Kind of, if we look how these protocols are implemented, they are implemented on some hardware which kind of has trends of multi-core, kind of how to make use of more available silicon space. Yes, we add more and more cores, and of course this makes our task more difficult. To these kind of multi-core or many-core CPUs, we attach network adapters, but there is not a single data flow. We now have multi-queue network interface cards, and even worse, we have network interface cards with quite some complexity to speed up certain things, but which also cause some effects. One example being what Netronome provides with their SmartNIC network flow processor approach. Then we have nice switches, which kind of are attractive by their features and programmability, and kind of barefoot networks. P4 is one example. And my statement here is we didn't even reach the full complexity introduced by that additional level of programmability. And this gets combined with software complexity, kind of a couple of approaches to achieve high performance, such as Intel's Data Plane Development Kit, DBDK, or NetMap, or Lua-based network function chaining based on Snap. There are different virtualization approaches, Xen, KVM, etc. There are container approaches for lightweight partial virtualization, like Linux NetSpaces and C groups, all introducing additional performance artifacts. Now let's look at some of those in more detail. So this would be an architecture of a typical 2 CPU multi-core server, which in many cases is used for processing protocol stack plus some networked application. And at the end, we frequently ask ourselves, why do we see certain behavior? So we should understand the specifics of this architecture. Like, there is a cache hierarchy, very fast but small, level 1 cache, larger level 2 cache, larger level 3 cache. When this is not enough, access to the much slower RAM or main memory is acquired. Then we have network interface cards attached to them. Sometimes some software is executed here, but the data arrives here and needs to cross this interconnect. So, for example, if we want to understand performance properties of some layer 2, 3 device in the network, like Open vSwitch, we would see there are different ways how data paths can happen. So data can arrive in the best case in this way and leave via the same attached NIC. We could have cases where the software gets executed on a core here, and have to traverse this internal connection twice, or only a single time? And does it make a difference whether we first process it here or first forward and then process? A lot of questions. What's the right approach to answer them? How to set up the experiment? And this is not the only kind of complexity we have to deal with if we want to understand what's happening with a fairly simple piece of software like Open vSwitch. There are also this kind of interactions in the software space. So we would have a kernel space where kind of device driver and operating system play a role, but then a lot of speed up got achieved by having user space processing, where here DBDK directly forwards to the application, which is possibly in a virtual machine. So these are kind of the approaches that did allow like an order of magnitude speed up if we bypass the kernel and directly go from the NIC to the application. But at the same time, this introduces kind of new possible bottlenecks and effects to be understood. Now, a bit earlier I talked about many core architectures. So one example would be Tylera, which had a range of CPUs like 16, 32, 64 cores. And they are connected by some internal interconnection network. And for example, if a company, like in this case, MikroTik, produces a router which benefits from the high processing capabilities, well, some packets get forwarded by being processed in such a core which is easily reachable. Other packets get processed by some core that is further away, and therefore we see different performance. How to set up the experiment, how to interpret it correctly. And this is not enough. Kind of what we have nowadays with smart NICs, like in this example, Metronome. So on a high level, the architecture looks like this. We have this flow processor that is attached and speeds up the multi-core CPU. But if we zoom into the details, we see a frightening complexity. So we have different packet processing cores and flow processing cores and complex hierarchy of memory, and depending on where which data is located, we will have different access speeds. So we should be faced with, it's kind of impossible to model this properly which bottleneck occurs. So hopefully our experiments will have all the relevant cases in the data, and our machine learning allow us to deal with that. At least this is our hope. Now, I had talked about programmability. So here we have an example of the P4 kind of quite loved approach. So we have match action tables and pipeline. We have a configuration based on different programs. We can implement such an approach either in hardware, like Barefoot Tofino's product, or we can have it in software. And now the big question is, what is now the performance properties we can achieve? When should we be prepared to hit which kind of bottleneck? My assessment here would be, so far we research focused on functionality, and it will keep us quite busy for a while to also understand the performance issues and deal with them successfully. Now that I kind of explained our view on the problem area, let's explain a bit why we still think there is enough hope that we can solve it and achieve enough meaningful data. So we said kind of we have to support the scientists that do the experiments by a good environment. and what constitutes a good environment. So we did set up a test bed with the aim of reproducible capability. So kind of we said, let's build a workflow where we have test configuration and then scripts that do all of these steps, like allocate the needed resources for the experiment. So here we see our pile of hardware. It's kind of heterogeneous, so we have different network adapters, different servers with different architectures, so we can investigate the different issues. And it's kind of the experiments happen by explicit connections where only test traffic flows, and then we have an additional connectivity to manage the experiments. Then we go through a workflow, we boot the test machines with the right software version, which then also gets documented, which experiment was done with which type of software. We deploy images, configure the topology, run a couple of tests, iterate on the relevant parameters, collect the results, and do this. So this helped us a lot, this systematic approach. Then I would say it also matters what components we use in such a test bed. For example, how to generate the test traffic. There is one kind of industry standard approach. Let's use dedicated hardware traffic generators. They are nice because they are fast. Yes, they have some drawback because they are expensive, but maybe we have the money. Are there more drawbacks? Oh, it's not so easy to work with them. It may be a real nightmare to make them do what we want them to do. They're also not flexible. Sometimes the experiment we want to do was not foreseen by the manufacturer, so we may face some impossibility to do certain experiments. They are precise, yes, but now the question is, can we do better? So we did believe in kind of the progress of commercial off-the-shelf hardware together with smart software. So we said, let's build a software traffic generator and let's see how far we get. So being fast, DPDK allows for that. It's inexpensive because commercial off-the-shelf, high volume hardware is used. We have simple software setup, so it's easy to deploy. It is flexible, really flexible. We can craft our own packets. Our traffic generator, MoonGen, the name Moon comes from Lua because it's based on the programming language Lua. It's script-based, but kind of fairly nice language. Question is, how about precision? We looked at it and we were, at the end, after some improvements, we were fairly satisfied with the precision we got. But of course, there are issues to be looked at. One would be kind of, what can we do? How can we use the capabilities of the hardware? And luckily, companies like Intel built a lot of dedicated functionality into the network adapter, so we can use hardware features for time stamping and rate control. But kind of there are also some limitations of, for example, which way of rate control the hardware supports. So there is a need for a flexible one. So we kind of came up with an interesting approach. But first, let's kind of look at the pure software-based precision and accuracy. So we compared a couple of software traffic generators. This would be 500,000 packets per second, 3 tools, and each of them would be configured to kind of with the right time interval. If we have 500 kilo packets per second, we would have 2 microseconds in the packet arrival time. Ideally, all observations would be here. Now the kind of, we have some issue with precision and some issue with bias. The question was, can we do better with pure software? And Paul Emmerich from my group came up with a dirty trick. So he would say, let's fill the gaps between the real packets by dummy traffic, which has invalid CRC, so it gets discarded at the receiving NIC. But we have a real good precision because we can just, on a per byte level, control the inter-packet gap. And we compared this approach with FPGA-based traffic generators by the Cambridge group of Andrew Moore, and we were quite happy. So this kind of is the distribution of the inter-packet gaps of all the software approaches, and this is when we use this kind of corrupted CRC in the packet gap being filled. And here, kind of, if we have a different target rate, kind of we did observe different relative errors, like some software traffic generators we could say are really bad. And if we have such data, for example, as the basis of our machine learning input, we shouldn't be surprised if the results are not as we want them to be. And what we see is, okay, if we do it right, we can set up experiments with high quality. Now let's go further. What are we interested at the end of the day? Understanding root causes of performance issues. This means identifying the different bottlenecks. What are they? So if we look at a certain hardware, there are possible bottlenecks being the network bandwidth. If there is some processing on the network interface card, this can be the bottleneck. The PCI bus bandwidth can be the bottleneck. The memory bandwidth, when software is executed on the CPU, which has to access data in the main memory, can be the bottleneck. Then the different cache sizes of the cache hierarchy can be the bottleneck. And there are also effects by the cache line length. In addition to this list of hardware possible root causes of performance anomalies, we should look on the software, which is the CPU utilization per packet and what happens with kernel and network stack overhead. So when investigating this, there are two classes of approaches. One would be, we do a black box investigation of our device under test. So we generate load and send it through the device under test and observe what we get, thereby measuring throughput in terms of what. These are now the KPIs which are of relevance, like packets per second, frame loss rate, or burst behavior. And of course, latency matters, so we need to have tools that are precise in measuring latency. And if we want to understand more, we have to go to a white box approach, where we look into the execution of the software on the target hardware in order to understand hardware and software events, interrupts, cache misses, and the needed quality per second, per byte, per function, etc. Let's look at some examples. One example was investigating a software router, in this case FreeBSD based, with worst case traffic, which for a router is very short packets. And then we observed the latency. So we got a mean latency, which is nice. It's only kind of around 7 microseconds. Quite good. Now, if we have some end-to-end requirements, it's also the distribution which matters. And in this case, kind of you don't see it well because here is a linear y-axis. We do have, unfortunately, a long tail. And so one important point, the average doesn't reflect this long tail. And we always have to understand the distribution. So this was kind of a not surprising distribution, but we also had kind of experiments where we were surprised on the first hand. For example, there are nice switches, PK8, SDN switches, and they showed the following behavior, kind of a bimodal distribution. So the average it's very rare that we see packets that have really the average latency, because kind of there are different processing paths through the device, and so either it's very fast or it's much slower. And kind of by investigating this as a human, if we get presented histograms, we immediately understand it. Kind of if we evaluate, it's also useful to define percentiles and look in which way they differ. Now let's look at another hardware architecture, many core. I had introduced the question, kind of what's the effect of such a interconnect on chip? And here we see it. It's a kind of a pyramid style around the average, which starts at a certain point, and in this case it's symmetric, so obviously the software was good in the sense it did load appropriately all cores, and it shows a very specific behavior for this target architecture, which was kind of a software router based on this many-core chip. Now, what can we do beyond by using a white box approach? We can really understand kind of in processing, for example, IP forwarding, what needs to happen, and what are the kind of environmental conditions that affect performance. So first, let's look at the software architecture. So this would be a Linux software router, and we can kind of see packets get handled by a couple of subparts of the code. And we could ask ourselves, what is the cost of certain tasks in this chain per packet? And which costs increase in which way when we increase the load? Because it's not all the same. And then we can ask some protocol specific questions, such as if we have IPv4 and IPv6 traffic, where is the difference? But of course, we will have a long list of similar questions. One way to investigate this is a tool called Flame that produces such type of output. So this is a visualization where we call kind of this function, and this function calls another function. So the real execution time is kind of hidden in where there is nothing above. And such a thing needs to be processed further to get the real understanding. So here we kind of, we looked at such flame graphs with for different load, and kind of the different processing is shown here. A lot of small stuff is in the gray, and the idle is the dark gray. And then how to model it better to get a better grasp on what we have here. So we did group the functions into pre-routing processing, a couple of things. Routing subsystem, this is where the forwarding table lookup happens, which kind of is a relevant issue for software routers. Do they scale sufficiently? And depending on how we configure our device, if we also do firewall functioning or similar things, other parts may dominate. Now here are kind of some results for of this white box approach, looking at the left at IPv4 traffic and at the right at IPv6 traffic, and kind of the device under test was loaded with a different number of flows. And if we have kind of 1 million flows, then the lookup will be much more intensive. And kind of the shape here is similar concerning this routing or lookup part. But if we look at the y-axis, we see that this version of Linux was able to handle v4 traffic with 1 million flows with much fewer CPU cycles per packet, like around 500, while here it goes up to 2,500. So kind of this would be one typical insight gained by having the right type of experiments that yield with the right data. Then let's look at this different cache level impact. So for that, we performed some experiments with the SNAP framework, Lua-based network function chaining framework, and kind of we created an artificial forwarding function which would have different type of loads. Either it accesses a data structure 100 times or 200 or 400 times, and kind of then we varied the working set size of this data structure linearly, did a large range of experiments and looked what's how many average cycles per packet do we have. And so this is 10 to the 5 here. And what we see here is kind of a couple of steps. If this working set size fits in the level 1 cache, we're really fast. If it fits in level 2 cache, it's a bit slower. Level 3 cache, again a bit slower. And if we access main memory, this is what slows us down by a factor of 5 additionally. And this means kind of the specifics of our hardware architecture will really dominate these processing costs. So we should understand in which way the data structures fit into our hardware architecture. Okay, so all these experiments have been done with our Lua-based traffic generator, Munchen. We thought, oh, this is a nice tool. And then we thought, let's kind of make it, let's try to use it for different applications by making an interface kind of, so we, based on Munchen, libmoon was created, which allows to build arbitrary functionality on top of it. So this means we have a straightforward, simple, flexible way to use DBDK by having a wrapper and having Lua scripts and some support libraries. And we built a software router and a solution for flow analysis. And the statement would be more things that help to collect relevant data can be built with this tool. So it's like it was very useful for us for making advances in research. So the architecture of this moon route router would be, it's targeted for a multi-core architecture. We would have all the complex stuff of the protocol, of the routing protocols like BGP being executed by Linux. That exports the right tables, and then we have two types of implementations. The fast path is just forwarding IP packets. Of that we have many. And then slow path is ICMP processing. And we do dispatching of incoming traffic using receive side scaling. And so kind of, it's nice, fairly straightforward, and because it's with Lua, it allows us to replace like one lookup algorithm by another one and investigate the effects. When we looked at the performance, kind of we compared it with other software-based approaches, and kind of we were quite pleased about the performance. But of course, kind of some are much older, so the comparison could be said is not completely fair. But by such an approach, even if it's Lua-based, we are kind of mapping, using DBDK in the right way, we can achieve really nice performance. Now this other tool, FlowScope, there we said, let's look for how to be able to record traffic that arrives with very high speed. We will hit the capabilities of what we can buffer in a usual server, but we want to pick the data of relevance for us. And relevance does not need to be known a priori. We can have some complex algorithm that just picks what we think is of relevant at that time. And then we analyze it and maybe store copies or just store the result of our analysis. And kind of we made use of a special data structure, a queue of queues, which kind of trades off throughput at the cost of latency, which in this case, it's not a latency critical application because we hit throughput limits. And kind of when comparing this data structure kind of in achievable packet rate with some other ones, yes, this helped a lot to achieve the high performance. And kind of my assessment of this approach would be these properties, being able to pick from high traffic volume the relevant ones, allows us to collect high quality data of appropriate scope. So it's useful. We try to get an understanding kind of where is this approach useful with kind of work with libmoon. So we built some high performance applications, FlowScope and Moonroute. We built two benchmarking solutions, one for switch benchmarking and one which is kind of a workflow to perform the performance benchmarks as stated in RFC 2544. And the OpenNFV community also built a automated NFV testing framework based on libmoon. And then we looked at who uses the approach in their research, and we found quite a number of work by others that used it successfully. And there is some work in assessing the kind of quality of the tools in terms of precision and accuracy. And yeah, so we had one ComsNet invited paper where we tried to give this overview. So this would be kind of our explanation how to achieve high quality observed data in a very controlled environment. Sometimes we need to deal with a more complex environment, like, well, maybe we want to use existing appliances, dedicated software that has some complex user interface. So we also looked at what would be tools to set up experiments in such a way. So again, having scripts and automating the configuration helps a lot in getting good data. Now, I want to talk a bit about kind of this aspect of global significance. So when I said kind of what's the scope of the data, if it's relevant on a global viewpoint, we could say, are we able to collect the data that is representative for all servers of this type? For example, for all web servers, all SSH servers, and so on. And luckily, kind of as a research group, it's already, you don't need a lot of resources to just crawl all web servers for their TLS certificates. So if you do it systematically, yes, you can collect data of global significance. And so we applied it to a range of protocols. And I just want to pick the TLS work as one example. So we said in order to assess quality of certificates used for web server protection, we should both do active measurements, just do the handshake, collect the certificate, but also kind of look passively what happens. So a couple of years ago, we already did this systematically, also over a longer time period. So we were able, like some servers vanish and reappear. So if you do it systematically, you have kind of the data of global significance. We used it to assess the quality. In this case, kind of it was certificates, so people can do a wide range of stupid things. Like a certificate chain can be broken, host names may be mistyped or missing. They may use the same key for different certificates. They may have generated the key in a stupid manner, so they are weak and can be broken. And kind of by having the full collection, we were able to group. In this case, grouping by Alexa top 1 million rank. So one assumption could be, if you operate services that appear in the top 500 list, you have professionals and you do everything correct. At least this was, this investigation showed this is not the case. But okay, this is reality. Like administrators always do one of the following mistakes with the following probability density distribution. This is one of the lessons learned. So this data can help us to reveal such insights. We also looked a couple of years later, kind of there are a number of TLS enhancements to protect against certain attack vectors, which would be TLS downgrade, TLS stripping, man in the middle, with either, for example, fake certificates, misissued certificates. And then there are a couple of techniques that protect against certain of these attack vectors. You could apply all of them for your web server. What would people do? In which way are these techniques adopted? And when we have a global look at it, does it make sense what people do? Or are they maybe just lazy if they don't adopt? So kind of here we looked which combinations of these techniques can be observed, and kind of certain things are really rare. And then we kind of combined it with an assessment. How much effort is it to use, if you're operating a web server, one of these techniques? Some are very simple, some come with a high effort, but this is not the only dimension to assess. There is another dimension. How high is the risk that if you do a mistake, that your service gets kind of not accessible by your target community? So some techniques kind of are low in effort and low in risk, and they are, as to be expected, widely adopted. And for others, one could say those who specified it did not use sufficiently the understanding of the operating community about how high is the effort and how high is the risk that you may become inaccessible. And then just much later, people complain, the stuff doesn't get applied. Okay, so this would be kind of some examples of how to collect data of global significance. Now let's take an outlook about, from my perspective, what would be important to do in the future. So from my perspective, there is a lot to be done. Like we have many questions about performance properties of specific technologies, and a wide range of possible limitations. They could come from the hardware, the software, or the protocol stack and configuration. In my talk, I showed there are, from my viewpoint at least, sufficient methods to collect data with high quality to answer this. And then we can ask ourselves, which are the possibilities by using machine learning techniques to answer these questions to our satisfaction? Where are the limitations of specific machine learning techniques? I'm kind of going back to my introductory thesis, we should not try to answer these questions about suitability and limitations of certain machine learning approaches unless we are convinced that the data we use is of the needed quality. Otherwise, kind of the outcome will be not representative for this method and approach. I can ask a couple of more specific questions, like we would like to do analytics for networked systems, being able to do what-if analysis, like if we would do some change, what will be the performance impact? If we want to improve our dimensioning, how to do it? And if we have issues, what are the root causes? So hopefully, based on some system, we were able to predict what happens if we do some change on it. And this kind of leads me to my conclusions, and hopefully will steer some follow-up discussions. So I talked about what are the issues if we look for scaling up packet processing. I said there are a wide range of factors. In order to understand them, we need to do the experiments in the right way, collect the right data, doing it in a replicable and reproducible manner means doing a lot on automating the test setup and proper documentation. And I said, data quality matters, and in particular, the following dimensions matter. Precision and accuracy, so we should use the right tools. Coverage, did we bring the system in the right state that the relevant bottlenecks did show up in the data? So we like using artificial load in the right way when we understand where could be the bottlenecks will lead to the right data. And scope, like is what we observe of relevance for others? Yes, if it addresses general, globally observable properties by the hardware, by the software, or by anomalies that are representative because they're done over and over again by humans when configuring the systems. Okay, so these were my conclusions, and hopefully I steer some questions or discussion. Thank you.
Okay, so here's time for some questions. Anyone from the audience? What I can start? Okay, so actually, you really made a case when you did a PhD from Munich to understand all the nasty details of the system, right? I was wondering, the system is so complicated that mastering all these details requires a lot of time. Right? Also in your models, you were going down to the single queue and so on and so forth, but you're still high-level models. CPU, for you, it's a CPU. Whatever it does inside, it's a black box. I was thinking if machine learning, which aims at building models from data directly without having the knowledge of the phenomena going inside, could actually help in simplifying the models to predict your performance or so. Yeah. This is something you were mentioning at the end, right? Yeah. Do you have any experience with that already, or?
Not yet, but kind of my main statement would be machine learning can help us if we manage beforehand to generate the right data. This means maybe we don't need to understand all the nasty details in all their implications, but that they are there and that we applied enough thought when setting up the experiment. That way we triggered all this happening around all the possible effects. And so my statement would be, you need deep domain knowledge when designing your experiment.
You still need a PhD from Munich?
No, I would say kind of, well, it's an open question how much you need. And probably we need further examples of different people generating data sets by different ways, maybe a much simpler one. Kind of course, it will be nice if you come up with a fairly simple way to generate meaningful data. But still, already your simple way needs to capture all the relevant effects.
How many of your experiments, papers, and work is actually reproducible? People can reproduce it.
If they can, well, so far, I think we don't have in our community the tradition that other people try to reproduce. So, kind of, there is some work on looking at the precision of the traffic generation process, and I would say people usually try to look at a bit of different things. So the main purpose was not just reproducing, but rather telling, okay, we want to look at another angle. So I would, not only our work, I think are you aware of papers that just try to reproduce other findings?
Not many, yeah, I would agree with you. And it's actually the complexity of the system, one of the factors that also limits the ability to reproduce the results. So for one of your work, you need this Stylera chip with this software, with this version, with this and that and that and that. Could I do it in my lab or not? How many, I mean, the system is so complicated that reproducing the same configuration with the same setup and so on may be even a challenge, because, I don't know, now I buy a CPU, it's different from the CPU you were using, right? So that is also something that is kind of limiting the reproducibility in our field, or not. The things are changing so fast and clearly there is a lot of effort in trying to do that, because it's not just buying the hardware, but I guess.
I think there we have a question of kind of global significance of the issue. Like the Tylera stuff, this is closed source solution by a commercial vendor, in this case Microtik. So we had some device they had produced in a certain month together with a certain software version. Of course, if you try to reproduce and purchase your own, maybe they changed something, or maybe they got some from Tylera something which is a little bit different. They may not know themselves that there is a difference. I recall from last year's SIGCOMM reproducibility workshop, there were some performance comparisons on Wi-Fi cards. There is also kind of a complexity nightmare. There are, on the network adapters, different hardware, kind of, the product may have the same number when you buy it, but the company may have used a different type of hardware, and it ships with some firmware version, which is maybe not even documented. And so we, as a community, I think we have an issue with that.
Yeah, I would agree. We also have the same issues with 3G, 4G mobile measurements, where you don't even know what's going to happen by the operator. They change the configuration and you don't know what's going on. And so repeating the same experiments is basically impossible. Okay, we have a question over there.
So first, thank you for your nice talk. Andreas Blank from Technical University of Munich as well. I have actually two questions. The first question, I mean, is about, you were talking about the precision. So precision on microsecond scale. Maybe can you elaborate a little bit on where does it actually matter? I mean, if I make some errors on micro precision scale, but I compare systems that perform different and on millisecond scale, does it really matter that I have these precision errors? And the second question is, you said like, okay, first generate data, then use it for machine learning. But have you also thought about like using machine learning to improve the data generation as well? So in the process of generating the data? Thank you.
Okay, there were mainly two questions. Kind of the first one, where does the precision matter? My statement would be, it matters where we want to understand a certain effect. So it may not matter at all on the average performance of something, but usually we hit some bottleneck at some difficult to predict scenario, and usually we want to understand the root cause. And if we don't have sufficient precision on certain things, my statement would be we are lost in general. Maybe not in a specific case, but it's kind of, we need to understand our precision. I think once we understand it and we can look at a certain question, we will be able to tell whether that is an issue or not. So I wouldn't talk of an absolute requirement of this or that, but rather kind of always be having the ability to assess our quality in the relevant dimensions for the questions we try to ask. And kind of, this would be for your first question, and for the second one, whether machine learning can improve the quality of the data. I would assume we can apply machine learning generally to all issues that matter, and so far it has always been a promising approach. And one question would be, in which way will machine learning improve beyond the current state of the methods without machine learning? So in that case, my first approach is always, how much can I do for improve like the quality of data by human intelligence? And then I can ask myself, in which way, for example, am I limited by my capability to deal with the complexity? And then I apply some machine learning, which hopefully improves, even if I can't explain why it does, because it finds some interesting correlation in the data and makes the right control that, for example, in this case, improves the quality. Yes, of course.
If I can add something, probably you can use unsupervised machine learning to identify outliers, and then use your domain knowledge to label those clusters of unknown outliers. That can probably supervised machine learning would be more complicated, because the model built by the algorithm typically is a black box, so unveiling something inside is very complicated. But it's actually interesting.
Yes.
Okay, here.
Hi, Lucas Kensel from Electrolux now. On one of the slides, you had a example of latency measurements where there were some outliers or some long tail measurements. Right? I've often seen papers where people tend to either try to smooth the data so that these outliers are gone, or they are simply not even considered being outliers. So I wonder if you can elaborate the consequences of that. If you ignore such data, what could be the consequence of the analysis?
What's the consequence of looking at the outliers,
of smoothing? So in what way will your analysis be wrong if you don't consider them?
Okay, thanks for the question. And I think the consequences depend on which question do you want to answer. Like if you're just concerned with average statements, you're allowed to smooth it out. But frequently, this is not enough. Frequently, you want to understand, may there performance anomalies being caused by this software router? And then at the end of the day, kind of this long tail has to do with, there are several million lines of code in a software router, and most of them is not touched in most of the cases. But it's not that they are always untouched. And And the software router is just one example. So we did build kind of with the internet and all the systems attached to it, something of frightening complexity, which may show behavior in a way that it's really hard to explain. And so the consequence would be, if you smooth it out and forget about it, kind of, I would say, sometimes you're really lost. So even if you can't explain which of the several million lines of code caused this long tail, at least you know that it is there, and you know when to dig deeper in case it may matter. Okay.
So let's take the there is a coffee break outside, and we get back here at 11 with the speakers. If the speakers would like to check the projector call, feel free to do this now.
I can't tell too much about very successful. Otherwise,
My question was actually very selfishly motivated because I'm just reviewing a PhD thesis where someone has done that, and I got difficult. And you need to say why is it bad. That's it's not so simple to argue. I say, yeah, like you said, okay, 5 minutes to images. So a lot of work you do at home. I haven't been there for a while. It's getting bigger and bigger, right?
and because there are several people involved, I think having software scripts that are reused, looked at by more. Yeah, I wanted to say, if I use the laser pointer, after some time it stopped. Probably the battery is too weak and you can replace it. Okay.
Our work that he has done on internship in Austria.
With who?
The Big-DAMA team.
Yeah,
What's the name of the person supervising you?
what's the name of what?
Your supervisor in.
I was doing an internship under Pedro Casas in TBN.
Oh, yeah. Okay.
So as part of it, we were just trying different string-based approaches and trying to move them from standalone environment and move them to more of distributed computed environment, which is well, there were a couple of frameworks used previously, but some of the projects it seems that they kind of stopped. So we see a chance or opportunity to continue where some of the work was extended. For example, there were projects like distributed Weka or Samoa, which were aiming for this, but well, actually I'm
actually released last year, and it focuses on machine learning and cloud technologies. He's going to present his work on machine learning-based network security and anomaly detection related. And this is a work he did when he was doing an internship in the AAT in Vienna, working with Pedro. So please, the floor is yours.
Thank you for the interaction. So first of all, welcome everyone. I hope, first of all, I'm not sure if the microphone is working. Okay. I hope you will like my presentation on stream-based machine learning for network security and anomaly detection. As it was mentioned, this paper was done by Pedro, Casas, and me as a part of my internship at AIT in Vienna. And this way I would like to also thank to OEAD Action Grant, which made it possible for me. So, first of all, the motivation, why we decided to write this paper. So, in this paper, we focused on stream-based machine learning. And stream-based, we understand analysis that is being done on one data instance at a time. The focus of this paper was finding out if the stream-based versions of the well-known algorithms are able to do comparable results, or able to get comparable results to their batch versions. In this paper we are using most recent evaluation approaches for sequential data, which include sequential evaluation and also AUC evaluation for sequential data. Obviously, one of the most advantages of the stream-based evaluation or stream-based machine learning is that we get less memory constraints, and we receive rapid processing, and we also are able to predict at any given time. But still, with these advantages, we are not sure how to choose appropriate machine learning model and which one is the best for the task. But as it was mentioned in the previous presentation, it's not only about machine learning, but it's also about having the correct data set or working with the correct data. So in our paper, we are using wide backbone network measurements, which are collected at the link between I think it's Japan and US. These measurements are publicly available. There are 15-minute network traces that are being labeled by Mavilab project. In the Mavilab project, they created taxonomy, which you can see on a slide. From this taxonomy, we are focusing on 5 different anomalies or AVEX. We chose these 5, the DDoS, HTTP, flash crowds, etc., as they are, to our knowledge, they were labeled with the highest precision in the data set. So out of this data set, in order to apply the machine learning, we are extracting the features. In order to extract features, we split the data sets into 5-second time slots, and this way we are able to calculate from traditional features, features like throughput, packet size, IP addresses, and then moving to empirical distributions, their percentiles, etc. The whole data set has 245 features, so well, it would be exhausting to tell them all. The data set is divided also to 5 binary classified data sets. So that's one data set per each attack. In these data sets, it's marked either as an attack or as a normal time slot. So from the machine learning models that we decided to evaluate, we pick these 4, KNN, Hoeffding trees, adaptive random forest, and stochastic gradient descent. The idea was that we were trying to keep in line with with previous results that we got in Big-DAMA project, and also these are well-known, well-studied machine learning models that are available in off-the-shelf machine learning libraries like MOA and Vega. So they are well-studied, well-known, and that's why we decided to use them with most recent evaluation approaches. In order to get some sense to the results that we get, we decided to study also the concept drift. We decided to use well-known, well-used paging linear test in process studies or time series studies. This concept drift test helped us to distinguish 14 different places in a data set when the statistical properties of data change, and that's why we are able to later on put some sense why the learning algorithms are behaving as they are. So in the evaluation, we use the frequential tenfold cross-validation and with the adaptive windowing and AUC. Frequential tenfold cross-validation is, well, comparing to its batch version, which is widely used. Cross-validation in stream-based uses k different models that are being evaluated at each time. So that's why when sample arrives, first of all, it's being tested, and then it's being trained in the remaining parallel models. For the AUC, this is the recent work that was done by Brzezinski and Stefanovsky. Hopefully I'm pronouncing the names correctly. They created in their work efficient algorithm that uses sorted trees. So the memory, algorithm uses constant time and memory. In our evaluations, is there any marker? Sorry, I forgot to ask before. Okay, thank you. So in our evaluations, you may see the dashed lines. These dashed lines are showing when the concept drift is happening. So when the statistical properties of the data set are changing. In this way we can distinguish between two machine learning algorithms that really make sense to be used for this data set, and that's adaptive random forest and stochastic gradient descent. As these algorithms are getting the results which are nearly the same as the batch results, which is the 0 marker, or even sometimes better. For the other algorithms, you may see that that algorithms are able to get even better results with regards to their batch versions, but they are really prone to concept drifts when they are happening in the data set. So you are not getting constant results, but sometimes when you have a data set that is not changing, maybe this could be a better choice. This way, this approach is the nice thing about the Advent approach is that you don't have to choose the sliding window. So Advent stands for adaptive windowing, and this way of evaluation can be used without any additional knowledge about the data set. So that's why you don't have to try different sliding windows, but you can have you can have results which are immediately usable. Comparing to this approach, when we evaluate the data set or the machine learning algorithms by frequential AUC, well, the AUC needs a sliding window. The sliding window is being we chose the sliding window as a fraction of the data set. And you can see that as the sliding window rises to the size of the data set, the results kind of smooth out, which kind of makes sense because, well, at the end, you are getting results as for a batch algorithm. But by fine-tuning the sliding window, you can distinguish between short or long-term changes which you might be able to track by different algorithms. So fine-tuning can help you to get the proper model for your task. And so in some conclusion to our findings, by fine-tuning the AUC versus Edwin, we are able to get more granularity in the results. But if you don't have any information about the data set beforehand, this could be a really hard task. We also received promising stream-based results for adaptive random forest and SGD, which is in line with our previous findings, but still it was nice that it was proven also by their stream-based versions. As I mentioned, with some fine-tuning or using the Edwin approach, we are able to get actually slightly better results for some algorithms than their batch versions, even though the general assumption most of the time is that the batch algorithms receive or predict better results than their stream-based versions. And this way, I would like to conclude the presentation. So if you have any questions, I would love to ask them.
Okay, we have time for questions. Anyone?
Hi, you have used several approaches for machine learning methods, but I think they are quite traditional approach. Do you have any reason you haven't used modern approaches like deep neural networks, such as CNN, RNN?
Like neural networks? Well, in this case, we were, well, one of the ideas was that we were trying to use the tools that are publicly available. And I'm not saying that neural networks are not, but they need much more fine-tuning. So the idea was to take something that is off the shelf, try to get the best of it, and see if the results are really getting better. So neural networks were out of scope for this work. We were focusing more on traditional machine learning models, not the deep nets.
Okay, any other question? So actually, if I got it correctly here, you have models that are updated over time.
Yes.
Did you also try to compare a system where the model is built asynchronously instead of continuously updating it, I don't know, periodically rebuilding the model, maybe in parallel, then loading the new model, or things like that, instead of continuously updating the model, tracking the traffic, and so on and so forth?
We didn't try this, but the reason is that from the top of my head, I'm unable to reference some particular paper. But what we saw is that the sliding window approach was studied many times, but the adaptive windowing approach was not. So we've seen in many papers decaying factor being used, decaying factor or sliding window for evaluation, but the more recent Edwin approach, we didn't see any results. I'm not saying there are not, we just have no knowledge about them.
Considering performance, do you think it's important to update the model in near real time, or one can think about building a model and then updating it sometimes?
Well, from our findings and also in my opinion, the Edwin approach makes the most sense because well, it takes into account the possible concept drift in the data set. Comparing to that, if you're using sliding window, then if something happens in the data set that, for example, traffic changes, traffic shifts, or something happened to some machine, it's unable to react as fast as Edwin. With Edwin, you receive some additional granularity when the window shrinks, and the model is taking only the most recent data into account.
Okay, thanks. Any other question? Okay, so let's thank the speaker. We now move to the second talk, which is again about anomalies in network system. The paper will be presented by Kazuki Otomo from University of Tokyo in Japan. He's actually a master student, so don't be so nasty with questions. And he's possibly thinking about joining the PhD program in University of Tokyo.
Okay.
So let's give him some chance to choose. Okay. Voila.
So, good morning, everyone. I'm Kazuki Otomo from University of Tokyo, and I'd like to talk about finding anomalies in network system logs using latent variable analysis. So we have this outline. So, you know, the system log is one of the most useful information source for troubleshooting network system or operating network system. So the some example of system log is shown in here, and as you can see, system logs is a free-form text format, so it is very friendly format for network operators. So we can know when and what happened in the network system just by reading these text data. So we can say system log is one of the richest and most effective information source for troubleshooting or operating network systems. But the amount of logs is rarely large because the network system is getting really large scale and complicated these days. And content of logs are totally different for each type of devices or each type of operating systems or processes and so on. So in a case of an academic network in Japan called SINET4, it has about 70,000 logs for each day, and it includes about 130 devices. So manually analyzing or inspecting these logs is very difficult or even impossible in practice. So automatically processing or analyzing these logs is highly required. So to do that, there are a lot of existing methods today. And almost all of them are relying on predefined log time series features or predefined anomalies. So it is because we have to handle a huge variety and large amount of logs. So if we use these existing methods, we have to do some data-specific feature creation process. I mean, it is, we have to do filtering or smoothing or denoising or setting proper threshold for the data set. So I think these existing methods have almost two problems. The first one is these methods are difficult to apply as a network systems. So these existing methods are working very well in the specific environment, but if we want to use these methods in other network systems, we have to optimize these methods, and it requires a deep domain knowledge about the dataset. And the next problem is these existing methods cannot detect unknown anomaly because these existing methods are relying on the predefined anomalies. So the goal of this work is finding anomalies from large-scale network logs and extracting useful information for the network operation. And we want to do that without data-specific processing. I mean, it is, we want to find anomalies not depending on the predefined features, and we want to find anomalies using unsupervised methods. So before introducing our proposed method, I'd like to clearly show about what the system log anomaly is. So let's suppose one example. This is cron log. And you know, cron executes the same process at the fixed time. So we can expect this type of log appears periodic. This type of log has periodic appearance. So this figure is an example of cron log appearance. And the very first log appeared at 05 a.m. and the next log appeared after 30 minutes. And as you can see, all the log appeared every 30 minutes. So we can see these cron log appear with 30 minutes periodicity, and this periodic appearance is normal state for this type of logs. So let's suppose the next stage rise hard. As you can see, there are some logs, and these logs appear every 30 minutes except the 235. So now we know the normal state of this type of log is 30 minutes periodicity. So this lack of periodicity is anomaly for this type of logs. We want to find these kind of anomalies. So the system log anomaly is deviated or unusual log appearance in this work. So to detect these anomalies, we have to get the normal set for each type of logs. And the real system log dataset includes a lot of type of logs. For example, cron logs or BGP state logs or remote SSH or OSPF and so on. And we want to find the normal state for each type of logs. So we estimate the normal state, normal time series trend for each type of logs. And we want to do that without specific processing. I mean, we want to avoid processing for each type of logs respectively. And after that, using this estimated normal state, we find the deviations from the normal state for each type of logs. So how to estimate the time series trend? So we use latent variable analysis. So latent variable is unobservable variables, and we consider the latent variable represents the time series trend. So let's suppose the previous cron log example again. We know this log has periodic appearance, and the July 3rd is one exception. So first, we translate each time series into latent variables. So now we have 4 latent variables. And these latent variables are vector values, so we can plot these latent variables in the latent space like this. And if we input the similar time series trend data, I mean, if we input the July 1st and 2nd and 4th data, these latent variables are located at the similar place in the latent space. So the normal state time series makes make a cluster in the latent space. So if we input the unsimilar time series data, I'm talking about if we input the July 3rd data, it will appear far from the normal clusters. So this is a deviation in the latent space, and this is the anomaly we want to find. So this example includes only one type of logs and only one type of time series trend. So if we try to use this method in real dataset, your dataset includes a lot of type of time series trend and a lot of type of logs. So using latent variable analysis, we can analyze all the log time series at once. So let's consider these log time series, and we can translate these time series for latent variables, and we can map latent space. And we can find some clusters in the latent space, and we also find deviations in the latent space. So we can find anomalies as the deviations in the latent space. So the important thing is we don't have to care about the actual behavior of each type of logs. It is we don't have to know what the exact time series trend is. Only we have to do is translating time series into latent variables and find the deviations in the latent space. So I'd like to talk about our proposal method. In this work, we use conditional variational autoencoder, as known as CVAE, in order to estimate the latent variables. This is an unsupervised deep learning method. And now we have raw log messages here, and first we translate it into log time series, and after that, using these datasets, we train CVA models, and after that, we detect anomalies. So first, I'm gonna talk about how to make log time series. So it has almost 3 steps. So first we have raw log messages. They are just string data. And first we apply a log template estimation method towards these raw log messages. Log template estimation is well studied, and in this work we use a method proposed by Kobayashi. And after that we can get the log templates. Log templates are structured format of system logs. So we can classify system logs by these formats. And after that, we further classify the logs by where the logs appeared at. So we call this group of logs as an event. So now we have a group of logs called event, and event is a group of logs including one template and appeared at one device. So we count the number of logs for each minute and split for each event, and after that we split the time series per day, and finally we got the 1 day long time series, and this is the log time series. So using this log time series data, we train the CVAE model. So we use a log time series, and we also use event IDs. Event ID is just an index of event. So we convert the event ID into one hot vector, and we input them into CVAE. So the event ID means what's the type of log and where the log appeared. And the CVAE has 2 networks. The first one is encoder network, and second one is decoder network. So we input the log time series and event ID into the encoder network, and the output of encoder network is a latent variable distribution. And the input of decoder network is latent variables that is sampled from the distribution that is encoded network output. And the decoder network reconstructs the time series. And CVAE tries to reconstruct these time series as close as these input time series. So in order to do that, CVAE computes the loss function like this, and then adjust the CVAE's parameters to minimize it. So after converge this loss function, we move to detection phase. So in detection phase, we only use the encoder network. So, and we input the log time series and the event ID again, and the output of encoder network is the distribution of latent variables. And we compute the Carle-Kleiber divergence between the distribution of latent variables and the prior distribution of latent variables. This value conceptually means how far the inputted time series is from the time series trend of whole data set. So we can measure the state of each time series using these values. So now we have, so one inputted time series is converted into one KLD values, and we apply clustering method or detecting anomaly detection method to these KLD values. And we can find the deviations by these clustering or anomaly detection method. So in this work, we use density-based clustering method called dbScan. So I'd like to talk about evaluation. So before evaluation, we did parameter tuning, and in this work, we use 10-dimension latent variables. It means now we have about 1,500 dimensions input, and using encoder network, we can reduce these time series into 10 dimensions latent variables. And we use a real system log dataset. It is 456 days long, and it includes about 35 million log messages and about 9,000 events. And in this work, we choose a part of data from the whole dataset. And the selected dataset include about 943 logs, and including 120 events. And we confirm this selected dataset include much variety of time series, so it is suitable for evaluating our method. So to evaluate our method, we also implement the PCA-based traditional anomaly detection method. I don't explain about the detailed implementation of this PCA-based method, but the difference is our proposed one using nonlinear mapping and PCA using the linear mapping. So we conducted these kind of evaluations, and I'm going to talk about only 3 evaluations in this presentation. So first one is precision. So to calculate the precision, we annotated all the detected anomalies based on the travel ticket data, and we also did manual inspection. And the true positive means the detected and also true labeled anomalies. So true positives are useful information for troubleshooting network systems. And precision is calculated by this equation, and the result is shown as in this table. Our proposed method detects 1789 anomalies, and PCA-based method detects 1825 anomalies. And the precision of our proposed one is 84.6%, and PCA-based one is 69.5%. So we can say our proposed method can detect the anomaly more precisely than PCA. And this is the number of anomalies distribution per category. The horizontal line shows the category of log type. This is manually annotated, and the vertical line shows the number of anomalies, and orange bar shows the CVA's result, and white bar shows PCA's result. So focus on VPN and PLS case. As you can see, CVA detects more anomalies compared with PCA. And investigating these anomalies, we can confirm CVA detects 280 true positives and PCA detects only 76 true positives. So that is CVA has robustness compared with PCA-based methods. So thanks to CVA's robustness against outliers, CVA can detect true positives. And next one is interface aggregation logs. In this case, CVA detects less amount of anomalies compared with PCA. And investigating these anomalies, we confirm CVA includes 75 false positives and PCA including the 180 false positives. So our proposed method can avoid these false positives, and PCA detects a lot of false positives. The detailed written in my paper, so please check it out. So last one is case study. We introduced two cases. So we briefly introduce about these two case studies. So first one is BGP state change logs, and travel ticket reports a connection with one neighbor AS got unstable on particular days. And our proposal method can also detect anomalies in BGP state change logs on same days. So CVA successfully detects these incidents from all the data set. And we also confirm PCA cannot detect these anomalies. And the next example is MTU reduced logs. So MTU reduced log means the possibility of unstable connection in the network. And usually this type of log does not appear. And if this type of log appears, we suspect some connections get unstable in the network. So as a result, CVA can detect these MTU anomalies and also separate them into multicast ones and unicast ones based on the difference of time series trend. So details are also written in our paper, so please check it out. So this is conclusion. As a summary in this work, we proposed a system log anomaly detection method using latent variable analysis, and we can find anomalies without data-specific feature creation. In this work, we use CVA and traditional clustering techniques, and we confirm our proposed method has robustness and low false positive rate compared with PCA. And in the case study, we show two cases. One is BGP connection and one is MTU reduced. So that's all. Thank you for listening.
Okay, we have time for questions. Okay.
Hi, could you please explain once more how the deep learning approach is combined with the clustering, the DB scan? There was one slide where you showed that the output of the DeepNet is used as an input from the DB scan. Could you please explain it more closely?
Okay. So the input of this neural net is the log time series and the event ID. This is the neural net's input. And the output is distribution of estimated latent variables. And the input of clustering method is this this Carle-Greiber divergence. And the output of neural net is appeared here, and this Fourier distribution is predefined, so we can calculate the this distance. And this distance is calculated by calculate for each inputted time series. So I mean, this time series has one KLD, and this inputted time series has one KLD. And these KLDs are input of clustering method like this. So we can find the cluster of this value and anomaly deviations in about these values.
Okay.
Hello, Michael Seufert from AIT. I have a question. Okay, you're using machine learning. We know we are in a machine learning workshop. That's quite good. But as you're dealing with the periodicity of the logs, have you thought of like using traditional methods like the Fourier transform, or maybe derive the coefficients also from the Fourier, derive the features from the Fourier coefficients? Have you thought of this, or have you tried this maybe?
So the focus of this work is we want to avoid using these Fourier transformation or linear regression methods. So because we have to adjust these methods for each type of logs, because the time series trend is totally different for each type of logs. And system logs include a lot of type of time series trend. So it is very difficult process, and it's not general process, we think. So in this work, we use latent variables and avoid using Fourier transformation or linear regression and so on. And after that, we can find some anomalies using this method.
Okay.
Interesting talk. I'm curious if the adversary knows that you're using this mechanism, how hard is it for them to change how they launch attacks so that you can't detect it anymore? Is it difficult for an adversary to get around your method?
Sorry, you're talking about how to modify our method?
No, how would if an attacker knows you're using this method, how would they change their attack so that you can't find them anymore?
Sorry, could you tell me other ways? I'm sorry.
So maybe the attacker, instead of doing certain events on a regular schedule, maybe they randomly select when they do things, so that it isn't so obvious that your method, I don't know, is it easy or is it hard for an attacker to change what they're doing so that they're still accomplishing their task, but you can't find them anymore?
So the behavior of attacking is changing in the time past. So this method is okay. So the latent variables are obtained for each days, and we apply clustering method for these timelines. It is time series of KLD values for each day. So if the behavior is changed, we can find these anomalous behavior in this time series.
So my guess would be that low rate attacks are going quite undetectable, while any change would probably be seen, because looking at time series, you will see a spike in some of the dimensions. how hard it is to avoid this, to evade this. The more complicated is the system you are designing, the harder it is for the attacker to try to evade it. So generally speaking, I would say this is kind of, is using a multi-dimensional, non-linear system, so quite complicated to reverse engineer and find a good attack, apart from the low rate that are there. So yeah, one last question.
Thanks for the presentation. I'm very interested in this topic. But my question is, you just focus on the metadata of the log. I mean, you just focus on the time series. That means when does the log appear, and if the log doesn't appear in this time, then it may be some anomalous behavior occurring, right? But we know that many logs just follow the regular pattern. The content of the log is much more valuable than the periodicity of the log. For example, I give an example. Suppose there is a monitoring log system which is monitoring the throughput of the server. Then we know that the normal state is the throughput is 10 GB. Okay, we see it is normal. Then the log periodically reports the throughput of the current server. Then after 1 second passed, it reports the throughput at 10 GB. 2 seconds passed, it reports that the throughput is 10 GB. Then 3 seconds passed, it reports the throughput becomes 1 GB. But you don't care about the content of the log. You just see, after 1 second, the log comes. After 2 seconds, the log comes. After 3 seconds, the log comes. Then you may think that it is a normal state, right? So in this way, the anomalous behavior is ignored. Isn't it the case conducted by your work?
So you mean I don't care about the content of logs
yeah.
at all? So I think in the system log analysis, of course the content of log is important, but today a lot of existing methods about analyzing system logs, but they also not care about the content of logs because the time series behavior is too various and too sparse. So detecting time series anomaly is even difficult. So considering the content of log is, I think, the future works.
Yeah, if we consider the content of the log, it may be much more complex, but the time series detection is much more easier, and I think it's the simpler is the most effective. So, yes, but I think if we can, following work, if we can combine both the non-content data information and the content-based information, that would be better work, I think. Yes, this work is very, very worthwhile. Thanks.
Thank you.
Okay, let's thank the speaker again. I guess you can apply for your PhD position. You survived. Okay, so last talk of this morning session, again about anomalies, this time on BGP. The speaker is Andrian Putina. He is actually graduated with his master degree from Polytechnic Torino. That's why I know him very well. He was one of my students. Then he moved to Paris when he started working on his PhD, and is now focusing on BGP anomaly detection and anomaly detection on screen projectors. Let's see.
Not working anymore. Let's see also this one. Okay. No.
Okay, so thank you, Professor Melia. I'm Andrian Putina. I'm going to present you the work I've done during my Master of Science thesis at Telecom Polytech together with Professor Dario Rossi and Albert Bifet, and in collaboration with Cisco. So network troubleshooting is certainly not a new topic in the community, and however the complexity of the network is increasing day by day, and for this reason, in order to ensure reliability, the providers have to constantly monitor their equipments. Nowadays, the monitoring is performed with in many different ways, as the simple network management protocol, BMP, or other many different active measurements. But there are still some limitations and in all these measurements. So for this reason, many companies, most of the companies are shifting their interest towards the so-called streaming of telemetry, which with respect to, for example, to the simple network management protocol, it's richer in terms of features. Indeed, it's possible to collect measurements per application, per interface, per protocol, with respect to the generic counters in the SNMP. It's possible to collect measurements at a very fast timescale in the order of the seconds instead of the minutes in the SNMP, and the features are described with young models, which are very easy to understand and interpret. Moreover, with telemetry, it's possible also to use the push data collection, which is robust, and you can have, for example, many collectors and use different subscription criteria. We have nowadays a lot of existing tools to collect, visualize, and maintain and store the data, as for example, Kafka, InfluxDB, Grafana. But there is still missing some kind of intelligence capable to process this increasing amount of data, not only to process this increasing amount of data in real time. And so we try to tackle this new challenge, considering a data center scenario in which we run real equipment traversed by realistic application traffic under 1 terabit per second traffic load, and over which we run real protocols as the IBGP, which is the one used for the routing protocol in the data, as a routing protocol in the data center. As you can see from the topology in the image, we have 15 nodes from which we extract the measurements at every 5 seconds, and we collect two kind of features from the nodes, which may be split in control plane and data plane. For what concerns the data plane, we have measurements as for each interface as data, as packets sent or received, bytes sent or received, or packets dropped, and etc. While in the control plane we have features related to the BGP, the BGP protocol, as for example number of non-paths, non-neighbors, number of update messages, and etc. So we, in all of our experiments, we thus collect a lot of time series, and we, from all the nodes, and we inject in the network some events which affect the routing strategy of BGP. We have therefore full control over our testbed, and indeed we generate the ground truth of all our experiments, and we annotate for each event we inject the type of the event, which may be BGP clear or port flap on any interface, and the node in which the event is injected. Moreover, we annotate the timestamp in which the event is injected, and however, we don't have certainty when the event may be considered ended due to the convergence time of BGP, which may take up to 5 minutes. And for this reason, we decided to consider an event ended 5 minutes after the injection time of the event. So we expect thus our algorithm to produce alarms only in the red area, and everything, all the alarms produced outside the red areas are considered false alarms. Our goal thus is to find an algorithm capable to detect events, the events we inject, and able not only to run in real time, but also to build and update the model itself as new data is available, and maintaining obviously a low false positive rate and a high recall. We will have used different strategies from both supervised and unsupervised approaches, but we decided to start with the unsupervised methods because our goal is to detect as many events as possible, and also because it is very difficult to perform a training session in such an environment. Because it's difficult to reproduce all the events. I don't know which are all the events, and we don't have existing data sets or labeled data for this kind of approach. So we started to take a look at the most known clustering algorithms, as K-means, DBScan, and others, but unfortunately, most of them are designed to work in offline mode, and they have also, for example, high complexity. DBScan has quadratic complexity, and which is not suitable for our purpose since we want to process all the data in real time. We thus find the dense stream algorithm, which is very similar to DBScan, based on a density-based approach, which maintains all the clusters in real time and in incremental way. And so we decided to build our approach taking as the architecture the main ideas of dense stream. So what is dense stream? First of all, dense stream uses a feeding function and fades all the samples such that the older ones are less important than the newer one, and introduces the concept of microcluster, which are defined by the weighted linear sum and the weighted square sum of the data point components, and the weight from which is possible to obtain the center and the radius of each microcluster. Moreover, each microcluster is defined by a key variable, which is the weight, and obviously the more samples a cluster contains, the more the weight is high, and it's possible in this way to distinguish between core or normal cluster and abnormal clusters by comparing the weight of each microcluster to a given threshold. As I told before, all the clusters are maintained incrementally when the new samples are arrived. And here I have a small example in which we can understand better how the algorithm works. And so, for example, we start all our experiments considering the first 40 samples as which are event-free by hypothesis, by construction, in which the operator can see the data and confirm that there are no strange events going on. And so we cluster together all the 40 samples and compute the main characteristics of this initial cluster. We compute in this phase also the parameter epsilon, which is the maximum radius a microcluster should have during all the process. So the idea is that every time a new sample arrives, the algorithm computes the distances from all the normal clusters, and it chooses the nearest one and tries to merge it to the nearest cluster. How? In this way. First of all, tries to merge it to the nearest microcluster, and by merging the sample to the existing microcluster, it compares the obtained radius, and if the obtained radius does not increase too much and is below the epsilon threshold, then the sample is merged to the normal cluster and labeled as normal. In this second example, we have again a new sample arriving, and the algorithm tries again to merge the sample to the nearest microcluster. But in this way, obviously, the sample is far from the normal cluster. So by merging it to the normal cluster, you have that we obtain that the radius increases too much, and so the merging phase is discarded. And obviously labeled as an anomalous one. As new samples arrive, they can be added to the normal cluster or to the outlier cluster. And for example, after we inject an event after the transitory phase, the system may reach a new stability point. At this point, we can see that new outlier samples can be merged together, clustered together, and when the new cluster obtained reaches the weight for which it may be considered normal, the algorithm transforms the outlier cluster in the new normal cluster, and so the model is built and it's updated, and this new normal cluster represents the new normal condition of the system. Obviously, we can't raise an alarm for each anomalous sample we may have in the system, so we decided to introduce the detection of order k, and in particular two of them, the temporal detection of order k, in which after the injection of an anomaly, we count the number of anomalous samples a node produces, and we raise an alarm only after the reception of at least KT consecutive anomalous samples. Obviously, also in the normal phase, we need at least KT consecutive anomalous samples to raise an alarm and have a false alarm. On the other hand, we decided also to introduce also the spatial order K, in which all the nodes work together, and we check if during a given time interval at least KS nodes produce an anomalous sample, and so we raise an alarm only if K nodes produce an anomalous sample. From an experimental point of view, we have performed several experiments in order to better understand and tune the parameters of the algorithm, considering both domain knowledge and experiment results. And we, after the experimental tuning, tried to test the experiments, the parameters we found during the tuning phase on a new completely independent experiment. And in the end, we've performed some preliminary feature selection. So, for the tuning of the parameters, lambda and beta, we used 3 datasets in which over which we performed the grid optimization, trying to understand how the results vary with respect to lambda and beta. And as you can see from the graph, we have that the performances smoothly vary on lambda and beta, but they heavily vary on KT and KS, which is very desirable because for us, the detection of order K are more intuitive parameters to set for an operator instead of lambda and beta. You can find more temporal interpretation in the paper of all the parameters. So, once chosen after the tuning phase, lambda equal to 0.15 and beta to 0.05, we decided to try the parameters in general the approach in a completely new and independent experiment, which is 2 hours long, and which contains 12 events. And the results show, as expected, that for increasing detection of order K, you can see an increase in precision and a decrease in recall. So obviously, K acts as a trade-off between precision and recall. but also in terms of delay, because as you can see in the detection of order D, we have that for k equal to 3, we don't have any more false positives, but we have an increasing delay, since we have to wait for at least k equal to 3 samples before raising an alarm, and we start observing a degradation in recall. On the other hand, in the spatial order, the approach may produce a lot of false positive for small k's, and moreover is not able to detect events which are internal to a node, since we need at least k nodes to detect an event. So, as a last result, we perform a preliminary feature selection, trying to run the algorithm using only the control plane or the data plane, and compare the results with the results previously seen. And when considering only the control plane features, so the algorithm is able to detect the event without producing the false positive already for the detection of order K2. However, this is expected since in the control plane measurements we have only BGP features, and we inject BGP anomalies. So this is evident that this approach is not going to work for other anomalies. So it's a very narrow approach. And for this reason, we run also the experiment considering only the data plane features, obtaining good performances in terms of both precision and recall for k equal to 3. And this is a very desirable result, because it shows that the algorithm is able to detect BGP anomalies without any kind of information from the BGP protocol, only from the data plane features. So we expect for this reason the algorithm to detect events from different protocols, as it is able to detect the BGP events we introduced. So to conclude, we have analyzed and customized an online clustering technique used as an event detection engine in a real data center scenario. And we have developed all the tool and the algorithms, which are available online, and the method has very low complexity, and it's ready for the operational use, since the code is available on GitHub, and also the datasets and the scripts used to produce these results. And you can see you can find all the datasets, the code, and also a demo of the algorithm on telemetry.telecomparitech.fr. That's all. Thank you.
Questions? No BGP expert in the room.
Yeah, it's not a BGP, let's say, method. It's not only for the BGP, it's for a method to cluster online the samples for every kind of measurements, numerical measurements at least. So it's...
Yeah, actually, I have a question. In your experiments, you had control on the network. You were injecting.
Yeah, the network is isolated, and
right.
We inject in leaf 2 and.
Okay, so you have a specific ground truth that allows you to label.
Yeah, indeed, in the ground truth,
right?
We label all the samples from the starting time to the ending time as anomalous, but actually we want only once to detect the event. So, for example, we count the number of consecutive samples, and if we reach 3, okay, for us that event was detected by that node, and that's how we build.
Now, I was thinking how realistic is this scenario if you think about a real network with BGP working and.
This
and
is
so
one thing. It's iBGP only for data center. It's very focused for data centers because it's not as the normal BGP. It's the normal BGP, but for example, in the data center, you usually don't have updates of new ISs coming because you have a maintenance. You have a schedule to update something, so it's almost not constant, but okay. You usually have.
You are in a simplified scenario.
Yeah, with respect to the normal BGP, for sure, because in the data center, if you have to change something, you have a schedule. Okay, let's shut down everything, do the modification, and then run again everything.
Okay, and when you use the data coming from the data plane, what kind of data were you using?
It's all, for example, for each interface, the packets sent or received in the last 5 seconds, or packets dropped. It's or the rate. So our time series of counters.
And why this is related with the BGP anomalies?
No, it's not related indeed. We have in the control plane. Why it's related? Because when you, for example, have a port flap, a link is shut down, so the traffic is passing over other links. So, for example, you will see in a link a drop in another link exceeding the maximum bandwidth.
So you engineer the features that are related to route changes.
Yeah, indeed. The features we're injecting modified routing strategies.
Because I was thinking the normal operation in the network, the load is changing because of application changes, because of
and we are working on this stuff. Actually, it's again a data center scenario in which the load doesn't change that much, but at least.
If you talk to people to data center, they will say no. That's not the case, but yeah. You actually see a lot of changes in terms of oscillations of load, because after a port flap you have oscillation. Okay.
So I don't know if I have here a slide with. No, I don't have.
Okay. Any other question? And considering methodology, why not using just batch processing for, I don't know, normal BGP, DB scan?
Actually, we were also using batch processing. And first of all, it's the complexity is higher. And we have some results, not here. The complexity is higher, and also the parameters in dbScan are the opposite of the one we have here. So for example, we have here epsilon, which is similar to epsilon dbScan, but it's not the same, since here we have microclusters, which are, if they are close together, if they are neighbors in terms of the center are in the distance from the center is less than twice the epsilon parameter, you can consider a unique cluster, while in dbScan it's complex to define epsilon, also for this scenario, in which here we have the first 40 samples. Okay, let's see the maximum radius of these 40 samples, and that's all for now. Then now we are working also on how to update the radius as the new samples arrive.
Okay.
Which is the future work.
Okay, we have a question here.
Okay, in your approach, you assume that the first 40 samples are event-free, and you cluster them as a normal one, right? And how do you get the number 40? And
sorry?
How do you get the number 40? 40, you assume that first 40 samples are event-free.
Actually, it's only a matter of, we decided to take, let's say, the first 5 minutes, and it's a sampling rate of 5 seconds, which is not 40, but we decided at the beginning 40, and we kept it. because actually it was in the first data sets. Obviously, the first data sets are not the best one, and we introduced the first event in less than 60 samples. So we decided, okay, let's go for 40, and then we have 20 samples of nothing, and then an event. In the last data sets, we have 200 samples before before you're injecting an event. So now we can play with 40, 55, 20, or decide to use something different from a unique number, a fixed number. So yeah, I know that's the complex part, which is the assumption is very strong at the beginning, telling, okay, 40 or that's all. This is the maximum radius, but we are working on this.
So there should be some domain-specific knowledge.
Yeah. The domain knowledge is obviously related to the 5 minutes of the conversion time of. We started from the 5 minutes of the conversion time of BGP. So that's why, and also because I'm not a network expert, but 5 minutes, it's a long time, you know, I think.
I just wonder, you are completely rely on kind of clustering. The question is whether you could generate some. You have done that. Some supervised events, so you can, based on those traces, to do supervised learning to be more effective.
Indeed. Indeed, the next step is the semi-supervised and a construction of a grammar. And we want to improve the sensibility of this approach in order to detect a lot of things, but then to compare what we have detected with the grammar and say, okay, this is for real something or this is not. So, for example, instead of using the detection of order 3, you use the detection of order 2, but then you have a grammar which compares with something you have seen before or not.
Okay. I think there are already some papers published on the BGP space to see some anomalies. So you could also try to see whether that can serve as ground truth for your training, right? Right.
Yeah, okay. Thank you.
No more questions? Okay, so let's stop here. Let's thank again the speaker and all the speakers in this session. I guess there is lunch somewhere, sometime. First come, first serve. So if we conclude first, we'll be the first one to get the food. We recover here at 2 p.m. and the chair will be Michael here, right? So if the speakers would like to meet him, he will be around here. Okay.
will result in a more efficient and safer street system.
Microsoft and this.
Okay, so I think it's about time to start the second session. So welcome back after the lunch. My name is Michael Seufert. I'm a postdoc at AIT, Austrian Institute of Technology in Vienna in Austria. And I will be chairing the second session. The first talk in the session will be NetSlicer, Automated and Traffic Pattern-Based Application Clustering in Data Centers by Liron Schiff, Ofrit Ziv from Gardikor, Israel, Manfred Jäger from AAU in Denmark, Stefan Schmidt from AAU in Denmark, and University of Vienna in Austria. The presenter will be Liron Schiff. You can already take your place. He's a chief scientist at Gardikor, working on data center security and SDN fast reroute and robust inbound control. Liron did his PhD in Tel Aviv University with Yehuda Afek and Anat Brem-Labar. And he had a research stay at T-Labs in Berlin with the Anja Feldman's group. So yeah, Liron, the floor is yours. Please.
Thanks for the introduction. I will describe NetSlicer. It's an algorithm for clustering data center machines into applications. And this is a joint work with Ofrit Ziv, Manfred Jäger, and Stefan Schmidt. We'll start by presenting the problem, our machine learning approach to solve it, the challenges we encountered along the way, our algorithm, some evaluation, and some example of use case. So when we observed the network of large data centers, if we consider all the logical connections or the TCP flows between all the machines in the data center, we get kind of a messy map. Inside it, there are actually all the network interactions and the activities of all the applications that installed in this data center. Just one word about the nodes in this graph can be either a virtual or physical machine or an internet host communicating with a data center machine. And it can also be an instance at a remote cloud. It can be everything with an IP address in the network. And it's very hard to see when we look on such maps to see the applications themselves. And this is important in order to understand the structure of the data center and to know which applications are inside. There can be many types of applications. And if we want to visualize it, to manage the network well, or to install security policies that will allow us to segment applications, it's very important to know what are the applications. And so if we want to group the nodes by the applications, we need some way to label the nodes, to know for each node, the machine, what application it belongs to. And in fact, labeling the nodes of a network is a bottleneck for doing network segmentation, which is a very crucial security policy for big networks. So one approach to label the nodes and to study what are the applications of the nodes is to use existing sources of information. For example, the orchestration system of the virtual machines allow us to attach tags and names to the machines. And there are also inventory system like CMDB, which allows to manage some description and labels for each node, for each device in the network. And there are also the DevOps scripts that were used to install the machines in the data center. So there is a chance we can extract from them some notion of what this machine is supposed to do, what services it hosts. However, these sources are often very limited. They can be limited in terms of availability. Not all of them exist all the time, or maybe they exist, but not for all the machines that we see in the network. There is also the issue of relevance. So sometimes the information that's stored in them is not up to date. So maybe it was, last time it was modified was when the machine was installed and the and the role of this machine was changed over time, but the sources of information were not up to date. And there is also the issue of consistency. So these sources may be updated by different users. Each of them may use its own way to express and name the machines. So there is no like standard way to give these labels in these systems. So what we worked on was a machine learning approach for labeling. So here we see like a simple example of a very small network where we have two applications, one on the right, one on the left. Each of them has several tiers. And our first task is to cluster the nodes into tiers, where a tier is a set of nodes with very similar connections, very similar network behavior. So if you can see these green vertical rectangles, they are like marking nodes of the same tiers. And once we found the tiers, we will cluster the tiers into applications, where an application is a set of tightly coupled tiers. This is actually a complete subsystem that has a very specific job in the data center. And another thing that we find is to identify the roles, like infrastructure and services types. This is some kind of functionalities that may repeat itself in the network. It's like saying that a machine is of type of database and what type of database, but this can repeat itself in different instances along the network. This is usually a simpler problem which can be solved usually by just looking on the port numbers, while tiers and application is a more it's a harder problem we try to solve. After we identify these tiers and apps and the roles, we want to generate simple labels, preferably human-readable strings that will make sense for the user that try to understand the structure of the network. And we give the names based, for example, based on the services that belongs to this application, or the machine names for all the machines that belongs to the same application or tier. So, for example, if we take this very big, messy map of a data center, after we identify the application and we group nodes to applications, we get a much more simpler and clear view of the data center. In this graph, it's the same network we just seen before, just each node here is actually a group of nodes of the same application. We also excluded infrastructure applications because they make a lot of connection to all the other applications. And when we have such a map, it's much more easier to understand the data structure, what applications are inside, and also to define security policies between the applications, and to restrict the communication between applications to specific ports that we think that they are required. So why is it a challenging problem? These are a few of the challenges we encountered. So first of all, in data centers, there are a lot of load balancing employed between tiers. So the services are very distributed, and clients, in a tier of clients, access a tier of servers, but because of load balancing, each server in the same tier may be accessed by different set of clients. So if you look on all the nodes in the same tier of servers, they're not exactly the same. They don't have exactly the same connections. Same for the clients. Another issue is that there are infrastructure applications. I mentioned them before. They add a lot of noisy connection, maybe in many ports, and they make the network over-connected, so it makes it hard to differentiate between the apps. So, for example, on the bottom, there is a domain controller that connects a lot of nodes from different tiers and applications, and we consider it as a noisy node. While, for example, the blue node on the right also have a lot of connection, but all of them go to the same tier. So this is not a noisy node. And another obstacle is the use of non-standard ports. So usually ports are very useful when analyzing network. It helps us to identify certain services and applications. And we also allow us to filter out noisy application, noisy services. But there are a lot of services and protocols that use random ports. And there are also the possibility for the operator to change the default ports from the default known ports for certain services and to choose a customized port number. Another issue is that we see the traffic that we can monitor. So, for example, in this simple network, we have monitoring agent in red nodes. So we mark with red the nodes that we monitor. And we can see the traffic between the red node and also traffic between red nodes to other unmonitored blue nodes. But there can be other flows that we can't see, like flows between blue nodes only. These are marked by blue links. So our information or our view of the network is not complete. Another issue is that we are talking about a lot of data. So there can be in a data center just getting bigger and bigger, and the number of virtual servers, because we track IP addresses, not physical machines, they're even becoming much higher and faster increase than the number of physical servers. And also, if we want to account also for traffic from the internet, then we also see IP addresses from the internet. So there can be thousands and much more of nodes and millions and much more of links. So now I will introduce our algorithm. It's like a machine learning scheme to cluster into applications. And the algorithm starts with an annotated graph. It's very crucial when analyzing the networks to pay attention for the port numbers. So in this map, this simple graph, the edges are colored by the ports, by the port numbers. And our algorithm continue and merge nodes that should be in the same tier or the same applications in 3 phases. So first, the simple part is to detect what is sometimes called clusters in the terms of data centers, which are distributed application set of nodes that communicate with each other. And this is detected by a highly strongly connected component in the same port. And this is like this red click on the bottom, or it's made of a lot of red links, meaning of the same port. The next 2 steps are more complicated, is to detect tiers, and we'll explain each of them next. So tiers we detect based on similarity between the neighbors, the neighborhoods of the nodes. And then once we found tiers, we cluster them into applications based on the connectivity between them. So here we can see the same network before with the tiers marked in green. One important property of tiers is that many times the nodes in the same tier are not directly connected to each other. So therefore we can't detect tiers just by using some connectivity-based measure. So therefore we use a customized similarity measure to detect tiers. And before stating the definition, let's start with definition of an endpoint. So an endpoint is a combination of a node ID a service port number, which is actually the destination port of the first packet sent in the flow, and a type, whether a client or a server. It's the type of the endpoint. So for example, if we look on this small illustration, and we list for some of the nodes, what are the endpoints they connect to. So let's look on, for example, on node X. It has it is connected to 4 endpoints. The first 2 are A and B at port 80 as clients, and the next 2 are to node D and E at port 21 as servers. We also use a weight function, which assign for each endpoint a weight with respect to some node. So for example, a simple weight function can be give for each endpoint the weight of 1 if it is connected to the node and 0 if it's not. We will later use another one. And our similarity is just expressed as a dot product between the weight vectors of the node. So the similarity between 2 nodes will be the dot product of all the weights they assign to each endpoint in the network, normalized by the total weights they assign. And so if we look on 2 nodes, for example, X and Y, the shared endpoints they both connected to, like the one shown in purple, they increase the similarity between them. They contribute positively to the similarity, while endpoints that are not shared between them, they decrease the similarity because everything is normalized by the total weight. However, sometimes there are nodes that we want to give them lower weight. Even though they are connected to some other nodes, we want to give them less weight, less important in the similarity. So for example, node C here, it may be connected to many nodes of different types, and we consider this node as noisy, and we want to express this and give it less significant in the similarity computation, for example, for node Y. So this endpoint appears for node Y, but we want to give it less significance that it's not shared between the 2 nodes. And we do this by definition of a noise of an endpoint. So a noise of an endpoint we defined as a maximum distance between any 2 nodes that it connects to, where a distance is just the inverse of similarity. And we give the weight to the endpoint to be the inverse of noise, proportional to the inverse noise. So as you can see, there is a bit of a problem here because similarity is dependent eventually on noise, and noise is dependent on similarity. Therefore, in our algorithm, we compute one from the other using several rounds. So with this definition of similarity and noise, the procedure for detecting tiers is an iterative process that goes several times. It computes similarity and noise, it merges similar nodes, and then do it a few times until there are no more similar pair of nodes to merge. Eventually, once we detect all tiers, our main goal is to detect the applications. So now we consider it as a different problem. Till now, we detected the tiers based on some similarity between nodes. Now we want to detect applications based on tiers, where application is composed of tiers that are connected to each other. So where we take the graph, where after we detected the tiers, we actually have 1 node per tier. So we can look on the graph of tiers. And on top of this graph, we want to merge the nodes to cluster them into applications. So each node here was a rectangle, green rectangle in the previous graph. So we give weights to the edges, where for each edge or link, the weight will be dependent on the endpoint it connects. For example, how many nodes were merged to each endpoint, and how many edges were merged, and what was the noise for the endpoints. Then we do very simple scheme with just to delete weak links, and then to cluster, to group together the connected components. Each of them will be considered as an application. So we implemented the algorithm in Python. We used a parallel design so that the heavy computation parts can benefit from multiprocessors. We allow the user to define some initial configuration to some cleanup of the data before. For example, some nodes that he knows that are more noisy, or some ports that are more noisy, so we can treat them differently. This will get the result faster and also give better performance. We also use some modular design. So when, for example, after we compute the similarity and we find similar node to merge, we can use different kind of algorithms to cluster them. Or once we get the tiers and we want to cluster them into applications, we can use different clustering algorithms. So regarding evaluations, we use data sets of 3 data center networks, which we monitor at core VMs. So again, we don't have a complete, but we see most of the connection in the network. We also obtain ground truth data regarding which node, which application is associated with each node. We did it using information from the operator of the networks and also analysis done by analysts. And these data sets are available online for everyone who wants to try themselves. And we compared our algorithm with mainly two clustering algorithms. One is Louvain modularity, and the second is not to vec, followed by hierarchical clustering and HDB scan. And we also tested some mixture of them. For example, running a net slicer for the tiers and then clustering the tiers using one of these two algorithms. For scoring, we use the adjusted random index from the distance from the result from the ground truth. So if we look on the result, on the left is the net slicer algorithm, so it performs the best and what we tested for most of the network. Another interesting thing to see is that for the third network, the yellow network, combining the net slicer for the tiers and then running not to vec perform a bit better for the third network. Another thing to see is that in general, the first network got better results than the other two. And we believe there are two reasons for that. So first of all, in the first network, the rate of single machine application, like application of size 1 is much lower. So the applications most of the applications have a non-trivial size. Moreover, in the first network, it's mainly used by a Linux operating system, so these machines, these servers are less noisy compared to Windows servers. And we also show them to analysts. We were very pleased from the results and are eager to try this on more networks. And now I want to show how this can be combined in a use case, in a real use case of microsegmentation workflow. So the operator will feed the net slicer with aggregated connections, connection monitored from all the network, and aggregated so that we will have only one edge per all connection of the same ports and endpoints. Then the algorithm will issue a suggestion for labels, which the operator can review and improve them, add more labels, or make fix if required. And this label will then be used to define a security policy. And this security policy can be written in a very efficient and faster way because they can use, it can be written in the granularity of the labels and not in the granularity of specific machines. So to sum up, the net slicer algorithm uses a customized similarity measure that is built for the cases we see in data centers. And it also uses another phase of clustering Z-tiers into applications. We have initial results which look very promising. And we have a design that works good for parallel computations and also allow to future changes. If we have time, I just speak very briefly about the future work. We plan to test it on more data sets, clustering processes running on machine, not just the machine, so we can allow different application per server. To try to mix the algorithm with more other clustering algorithms, and also to explore how many iterations required to get good results by the algorithm. Yes. Thank you.
Yeah, thanks again for the nice talk. I would like to have the first question, actually. Just a minor thing. You said the graph data, where do you get them from? Must they be provided by the data center operator, or where would you get this input to your algorithm?
So my company, Gardico, is actually doing security for data centers. So as part of the product, we employ agent and collect all the connection in the network in order to find attacks. So we actually build the data set ourselves.
Good. Any other question from the audience?
So one is a technical question and the other one is more generic. From a technical point of view, you use the dot product, right?
What, sorry?
The dot product
Yeah.
to check the similarity between two machines or so.
Yeah.
What's the size of the vectors there? Because to me, that grows with the number of machines in the data center and possibly with the number of ports,
Yes.
which means you have a huge number of dimensions. And there, the dot product probably will lead to noise. And so what's the effect of the dimensionality of each point in your data set? And the other question is how much of this can be generalized to other problems? How much of this can be applied to graph analysis, partitioning, and how is this related to that kind of work so that try to get main component, principal components in graphs and these kind of problems?
Okay, can you just repeat again the first question?
The first question was about the cursor of dimensionality. Yeah. And
yes, so I agree. This is a problem that vectors become long, and I think this is a general challenge we will need to face when we get to get it work on bigger networks and try to parallel this even more. Till now, it worked for a few thousands. I guess we will get to more challenges on the way. Regarding generalizing this to other applications or more generalized applications, so when we inspected other algorithms for clustering, we were missing a few things that we felt that were a bit specific for networks, like the port numbers. Although I agree, and I think I even found algorithms that work with annotated graphs. So we need to see. I agree, it might be able to generalize it.
I would have a follow-up question to the first question of Marco, actually. When you do this computation of the similarity and the noise, where you use the dot product, it's kind of this iterative, more maybe a fixed point approach. Did you check if this computation will always converge, or have you seen problems where this will not happen?
Yeah, so in the beginning, we had a few problems of convergence, so we used a few tricks. For example, we allow the noise only to increase during the computation. We started in the beginning with zero noise and then computed similarity and then a few times and only allow the noise to increase.
Did you try to make a mathematical proof that it will always work, or?
this is one of the future works to try to see.
Any other questions? No, if not, then let's thank the speaker again. Thanks for your talk.
Thank you.
And we come to the second speaker of the session. The paper now has the title Data Analytics, Service Composition and Deployment on Edge Devices by the authors Xiangxin Shao, Tudor Tiplea, Richard Mortier, John Crowcroft, Liang Wang from Cambridge in UK. And the presenter is Xiangxin Shao. I hope I pronounced the name correctly. He's a PhD student from Computer Lab in Cambridge University, supervised by Professor John Crowcroft. His current interest includes optimization of numerical systems and its application in high-level data analytics. So Xiangxin, the floor is yours.
Thank you for the introduction. And I'm glad to be here to present our group's work. It is a joint work by me and my co-authors and funded by EPSRC Databox project. Well, we have heard many quite insightful talk today about machine learning. And I think it is safe to say that the machine learning has dominated the field of data processing and data analytics. But with social awareness of privacy and personal data rapidly rising, it becomes kind of a social issue to both keep personal data private and benefit from the data analytics power of machine learning techniques. So some currently quite popular cloud-based machine learning services have some issues like communication cost, latency, and most of all, personal data privacy issues. So one current trend is to move the computation from the cloud to the edge devices. So many AI and machine learning services could be partly deployed on these user devices rather than putting everything on the cloud. And the use cases are numerous. There's automatic cars, personal data analytics in smart home, DNN on small devices, and network caching, etc. Well, there are already some systems that could be used to do the deployment of computations. For example, we have Clipper and TensorFlow serving for general model deployment. And we have the serverless paradigm, such as AWS, Lambda, and OpenWhisk for deploying functions. And also we have other systems, such as Laser, to deploy the specific kind of machine learning applications, such as linear regression. But the problem here is that they are mostly cloud-based systems. Although we do have some edge deployment systems recently, such as the Edge ML and Azure IoT Edge from Microsoft and AWS Greengrass, etc. They all has their own focus, such as reduce the computation complexities or reduce the size of the models or integrate it with the existing cloud systems. But there are still two challenges I think are not well investigated yet in the current literature. The first is how to reuse existing computation code. If you think about it, many data analytics services share common parts. For example, recommendation and image processing or translation. These services takes numerous efforts to train to get, but once they are trained, there is definitely no need to reinvent the wheel again. So how to reuse this existing code. And the second issue is how to easily deploy the same code to different devices. We know that the current IoT devices, edge devices, they have heterogeneous deployment environment. So it would be ideal if I can write my code once and deploy to all these devices, like everywhere. So let's dive in. But before I introduce the system we're proposing, I would like to say that we propose the zoo system. It is part of the OWL project. So it is a numerical library in Otomo language. So I'm not sure how many of us here are familiar with Otomo language. Okay, good. I think I should give it a brief introduction. So Otomo language supports functional programming paradigm, and it has quite powerful type system. So the OWL here is, I can say, the most powerful numerical library there is in the OWL community, in the Otomo community. And so OWL is a scientific computing system. It's designed in functional programming paradigm, and the goal here is to make it as concise as Python and as fast as C, and also have is type safe. So it provides a comprehensive set of classical numerical functions. If you will think about it as a NumPy library in the Python world, but there's much more we can do. So, for example, it also has a fundamental tooling for modern data analytics, including machine learning and deep neural network. It has the AD module. It has support for distributed and parallel computing and the GPU, etc. One of the vision of this OWL project is not just developing code, but to support both development and the deployment. I mean, I can write some code and deploy it to the cloud, the IoT devices, GPU, browser, Zen, virtual machines, etc. And so that's where the zoo system comes into play. So if you look at the infrastructure of the whole OWL ecosystem, at the low level, we have some the basic functions for n-dimensional arrays, or tensor as some libraries would call it. And in the middle, we have the classical analytics modules, such as linear algebra, the math, regression, AD module, optimization, etc. And the higher level, we have machine learning and deep neural network. And then we have the zoo to help to deploy all the development code used by the other parts of the OWL system. Now, let's see, here is the workflow of the zoo system we're proposing. Let's look at different components one by one. The first, initially, the design goal of zoo is quite simple, which is to make sharing your code, especially Otomo code, as simple as possible. So I think many of us here have heard of or used the GitHub gist, right? It's kind of a light-weighted version of GitHub, and every script you write is universally identified by a string of ID. So if we utilize this function in the zoo. For example, when I want to share my code with you, I can only need to give you one string of code. You can take that code and get my script, which makes the creation and the sharing of Otomo script quite easy. You can get this string of ID and use the hashtag zoo primitive in Otomo to import one whole script as a standalone module. So actually, you may say that with this basic function, we can already solve the first problem we proposed, which is to reuse existing code, right? We can have these different parts of code and combine them together using in the form of gist. But that's not quite the case, because we can't compose just everything. I mean, one problem there is to do the type checking. So to solve this type inconsistent problem, we introduced the service abstraction. So what is the service? It actually functions with type information. So it contains three parts. The first is gist, a list of gist IDs the service requires, and it contains parameter types of this service, and a graph structure that contains information about how the services are composed. It also contains some core operations, such as create a dictionary of services from one gist ID, and get a service from dictionaries by name, or combine multiple services into one. And here we have shown the signature information about the service. Now, let's come back to types. And we just said that we want we can't just compose everything. We want composition to be meaningful, to be type safe. So what kind of types are we talking about? There is this simple ones like float number, integer, boolean, string, and we have also some n-dimensional or tensor types, but that's still not enough. For example, you can think of two services, the one that output a PNG form of images. The other one get a, for example, JPEG form of image. Mathematically, they can all be represented by the n-dimensional array. But you can, if you cannot combine these two services together, you have an error because their file types are inconsistent. So here we propose to add some advanced types into the zoo system. Take the deep neural network as an example. So we think that most current deep neural network applications can be categorized into three different kinds: image, voice, and text. So for example, here we have defined three subtypes for the image, PNG, JPEG, etc. And we also define the two subtypes for the text, the English type text and the French text. You can easily add more if you want. And so that's the type system. Let's look at the example here of what I talked about. First, here is the basic usage of the zoo system. You can use the #zoo primitive to import a string of gist as a standalone module into your code. And so you can notice that we added some the VID and tool here. That is for the version control. You can specify one specific version, or you can add a threshold value to indicate how frequently I want to connect it to the remote gist server to get the latest code from remote. It turns out to be a quite flexible mechanism to do version control. And then this part shows how to do a service compose. We have used a small DSL we have introduced earlier to, like I say, here we get a dictionary of services from one gist ID, and then we get two separate services from there, and then another one, and then finally we compose these three services together into a new one. If we are happy with that, we can save that as a new gist. If not, we continue to experiment with this service. That's how this part works. And then after we are happy with what we already have, we compose a new service that we're happy with. And then let's turn to the next part, which is the deployment. And I think the key character we want to add to support deployment is to have multiple deployment backends. For example, here we add the support for Docker, which is a quite common method for computation deployment, and the JavaScript maybe not that popular, but it could be quite useful in certain cases. For example, if we want to deploy your code, your computation to browsers. And then we have Mirage OS. It's a library operating system which can create lightweighted virtual machines. It will be quite useful on resource-limited devices. And here is again the signature informations for this backend. We support 3 types of it, and each of them has generally 4 different steps to pre-process the files, to generate some build files, and then build the executables, and then post-process maybe, and to publish what we have generated. And here is a simple example. We have taken a gist ID. We specified the container name we want to publish to, and then we use one simple operator here to generate a container, as we have said, and then push it to the Docker Hub to be shared by other people. And so one thing to note here is how we separated these 2 parts. So when we were composing services, we do not care the backends it will be deployed to. And now we are do the deployment, we don't care where this string comes from. We just know that it's some service that is composed. And so next we do some evaluation on different backends, because in the end, if one of this method dominates all of them, then there's no point in choosing all of them. We can just use one, that's right. But there's some interesting fact here. So the variables here are, first, we have different kinds of backends. We have native code or bytecode in OCaml. You can choose either one of them. And in out itself, first we have the core library, which utilizes C code heavily to improve the performance. But there are certain cases where the C code are not allowed. For example, if we want to deploy our code to JavaScript, then it is not allowed to contain any C code. That's why we also contain the base library, which contains all the similar functions, but implemented in pure OCaml. So we have conducted some different evaluations. Here we show we have evaluated the performance of a map and the fold functions on n-dimensional array when we increase the sizes. And we have also shown the performance of gradient descent algorithm using the different combinations. And we also perform the inference on different deep neural network, which is not shown here. You can look for the papers for detail. And we compare the size of generated executables from this different method. And it turns out that we have different methods that have some, they can show some advantage in different cases. For example, here we can see that Mirage performs better than the others, but here we can see the base library outperforms actually should be faster our core library. So normally, and the JavaScript will be the slowest, which is understandable. But we also seen that it's the generated executable sizes. The JavaScript is the smallest. So all these different backends and the methods have their own strengths. So I think it will be an interesting topic to automatically find which backends, which deployment method will be most suitable for different deployment environment. And we have talked about some examples code here, but I want to show some like real-world examples in the next part. And one strength of Zoo is to minimize the code, to make it as concise as possible to perform the machine learning related analytics. For example, we have the image classification application here. I think many of us here are familiar. You can get an input as the image and then get an output as the classification string. We constructed it with our code. The code itself is also quite concise. And another example we want to show is the neural style transfer, which is you give it an input image and you choose a certain artistic style, and then the style will be applied to the image you inputted. And then we can see here is a code to run both of these applications with Zoo, which is very simple. Only lines, about 5 lines code to run each of these applications on your computer. I can show some online demo if we have time later. Suppose we have time. Okay, and okay, so here is a online demo I've created. So for the fast neural style transfer. So I chose a certain image as a style and another image as the input. And then we get the result in like 1-2 seconds. Also, we can change the style, and so the result would be changed. Yes, that's this application, and the inception image classification application are both implemented in our code and deployed with the Zoo. So as conclusion, I would like to say that we identified the 2 challenges of conducting data analytics on the edge. One is the service composition, the other one is the deployment. So to address them, we proposed a Zoo system that first provides a simple DSL to enable easy and type-safe composition, and then we utilize the multiple backends to accommodate different edge deployment environment. We have showed the expressiveness of Zoo with real-world use cases and evaluate performance of different backends. And so for future work, and I think we still have a lot more to do. And the first is to have some mathematical support for DSL itself, or extend itself for more operations. And the application here we have shown is mostly on the DNN, but for the application in networking, we still have to looking forward for more. And also, we have a lot of engineering work to do to support this, to polish the different backends. So that's all of my work here today. So thank you. Different questions.
So yeah, thank you for your nice talk. I would also start with the first question. So you said that with your Zoo framework, it's possible to send, let's say, scripts to an edge device. Yeah. So the question would be, how big is the framework which has to run on the edge device? So is it feasible to run it? Because the edge devices, they become even more and more power efficient. They have less or small resources. So how much requirements has your framework?
Oh, and yes, currently I think the emphasis is not on the resource part, how to say, and it's just on the composition and deployment. And I think there exists a series of technologies to minimize the size, to reduce the computation, especially for edge devices. We plan to add more about that in the next phase. So, yeah.
Okay. Any questions from the audience? I have another question. So the main purpose is somehow to also send, let's say, scripts or even machine learning models to the edge devices. And I think recently there was this Oracle graph pipe protocol to also send machine learning models to via networks. What's your approach on, or what's your position on that? Is it somehow a competitive technology, or is it a complementary technology, or how would you see the two options?
I think it's complementary each other. Say, like I said, is we currently do not focus on specifically for the resource and the computation on edge devices, but more on the principles of how to compose and deployment to the different backends. I think for their cases, they're more like focused on specific kind of backends or devices to processing data. But here, we propose the possibilities of to write this code once and apply it everywhere as edge devices. So I think it is more like a complementary relationship.
Okay. Any more questions? Maybe I have a last one. There was this evaluation plots you showed, and you had the time on the y-axis. I was wondering what time it is, which device or which processing time.
Oh, right,
could
yes.
you please explain?
It's actually this graph is conducted on a laptop, and we have also conducted the same experiment on the Raspberry Pi, and the result is similar, just orders slower, but the conclusion here are similar.
Good, and I think let's thank the speaker again. And this also ends the second session. We have now a very long coffee break. I think the keynote starts at 3:45, so meet you in 45 minutes here. Enjoy the break.
Microsoft and the city of Bellevue are
Okay, so welcome back to the last session of the workshop. We have the second keynote speaker, Ganesh, and his last name is like his password. Nobody can even write it, so I will not try to say your last name. Ganesh graduated from Berkeley, working on the group of Ion Stoica on Spark and Hadoop and parallelization and so on and so forth. Then he moved to Microsoft Research, where he's now doing a lot of work on video analytics. And he's going to tell us about his work on this, I guess, about how to bring video analytics to the common people and make it work for real, okay? So the floor is yours.
Thank you, Mark. And yes, to this point, I know writing my last name is complicated. The first year in the US when I filled my tax returns, I spelled it out wrong myself and I never got the refund. So yes, I can sympathize with that point. So yeah, today I'd be talking about democratizing video analytics. And at the outset, I want to make this point clear that this is not necessarily the same as video streaming as such in terms of YouTube and Netflix, but actually analyzing streams from these video cameras. This is a large effort that we have, and this is like the set of people, the researchers at Microsoft, the interns who've been involved in it, the faculty at other universities, and so forth. And the motivation for this work is frankly that cameras are everywhere. They're deployed by government agencies, they're deployed by private entities like retail, deployed for security and surveillance purposes and so forth. And the density of the cameras that are deployed is actually amazing. I mean, if you look at it worldwide, it's about a camera for every 29 people, which steeply drops down to like 8 in the US. And I believe the number is 7 in the UK. And you know, I'm sure we've all read like enough reports in terms of what people do with these cameras. You know, for instance, it's used to fight you know, surveillance, terrorism, and those kind of activities for security. The home is another area where cameras are getting hot. You know, home in terms of both the personal assistance indoors as well as outdoor, you know, sort of like calling bell-based stuff that detect, you know, the mailman coming and so forth. And including our own work, which was actually featured in terms of how you could use cameras that are there at these traffic intersections for traffic analytics. Let me play this clip.
Microsoft and the city of Bellevue are teaming up on a futuristic idea. They want to prevent bicyclists and pedestrians from being hit by cars before the crashes even happen. Cover 7's Jeff Du Bois is live in Bellevue for us. And Jeff, the project would use the city's traffic cameras.
And Michelle, there are 200 cameras that the city, with help from Microsoft, would use to help decide when and where bicyclists and pedestrians are most at risk. For instance, if it was being used at this intersection, the technology would be able to tell the city what time of day and which direction a bicyclist or pedestrian was going when they were hit or almost hit by a car. Traffic cameras in Bellevue already document drivers blowing through red lights at certain intersections. Watch this guy get T-boned after running a light. But for this new project, computer engineers at Microsoft are working on software that would analyze traffic camera video and could see when bicyclists are in danger. The program will, in theory, determine how fast a car or bike is going and predict their trajectory. According to the tech blog GeekWire, it's all math, algorithms to identify.
Cool, all math and algorithm, how hard can that be? Yeah. But I'm here to convince you that, you know, while a lot of the computer vision algorithms, which is focused on making a lot of these vision analytics accurate, that the problem is also that of being able to use them for analyzing real-time streams, which come at like 30 frames per second, and be able to do that with very low cost. And we believe that this would, you know, being able to do this would truly unleash the potential for video analytics, where anybody with a camera should be able to get benefits out of the video analytics and truly democratize it. So this talk would cover two main parts, and on one is on live video analytics at scale, where we embrace approximation, and the second one where we would shift gears a little bit to stored video analytics. And I'll finally finish with some of this work that you just saw in the video in terms of what we're doing with the deployment and traffic videos. So let's move to the first part. You know, so this is like the overview of the video analytics stack that we're building. Yeah, so right on top are the applications. You know, while traffic is one of the applications, the fun applications that we go with, the system itself is quite agnostic to what the high-level application is, where you know, each of these applications can specify their video queries, if you would, as a pipeline. There is a pipeline optimizer, in many ways akin to, say, a database query optimizer, if you would, that takes these pipelines and does the right choices. And then this pipeline, of course, executes on a geo-distributed cluster, including, you know, the edge cloud hierarchy. And so the first part of the talk would be a lot about the video analytics pipeline optimizer, as well as the geo-distributed executor. So this, you know, a pipeline is essentially a bunch of, say, vision algorithms, what we refer to as transforms or modules that are just chained together. This is an example of a video analytics pipeline where, you know, say, you know, videos are coming in, they get decoded into frames, and then an object detector identifies the objects, the moving objects specifically in those frames, tracks them across frames, and for things that are of interest, let's just count them. And, you know, for something like this, the thing that you would run into is is what we've often seen in a whole bunch of other systems, which is the curse of many choices that are available for each of these transforms or modules. If you look at the detector, there are like 40 plus implementation options that are available. And this is just a sample from a tracker challenge that I took. That was a 2015 tracker challenge. Likewise, for the tracker, which kind of like maps objects across frames, even more options available, and it's combinatorial, note that. And there are these implementations because each of them make different design choices. These are empirically made design choices, where they decide that, okay, for this kind of lighting, we need something new. For this kind of an angle, we need something new. And they consume, varying amount of resources, as I would show. But from an accuracy point of view, this is an example of two camera streams, of one camera stream, say, in Bellevue with object detection using, say, a classic background subtractor and a more, recent, say, DNN object detector, the YOLO one specific. You see that, in one of the cases, the background subtraction does pretty well, but not the object detector, which misses a lot of objects or draws the bounding box sort of incorrectly. But if you look at another camera stream in Bellevue itself, this time, of course, the stream seems to have much more of background and noise activity with people and so forth. The opposite trend seems to be the case. Who knows? Perhaps the background subtractor gets confused with a whole bunch of background activity. And these implementation choices aren't the only thing that you go after. There are more important knobs as well that you set in terms of the frame rate. The original streams for a lot of HD cameras is 30 frames per second. There is resolution of varying gradations. And if you put all of this together, right, these implementation choices, these knobs, what does it actually look like? These query plans, if you would. Since I called them the query, let's call these query plans, which is a combination of knobs and implementations. This is for, say, a license plate reader, an openly available option. Look at the x-axis, which is in log scale, and see how it varies with, each of these x's is a query plan as such, and see the spread in terms of the available, accuracies and CPU demands. And look at these 2 points, frankly, is they provide roughly the same accuracy of the output, and yet they're like 2 orders of magnitude different in the amount of CPU that they consume. And this is true for a whole bunch of other queries as well, which is with the object tracker. Again, the same thing, look at the spread, and likewise with, say, it's not just a CPU, but it's also a memory question often. And this is not like a static thing where, the best query plan that you select is going to be the best all the time. This often changes. It's dependent on the lighting, the color of objects, the density of objects. But I gave you the SQL analogy with a pipeline optimizer. But unlike the SQL world, there are no analytical models that we have that give you this relationship between the amount of resources consumed by every query plan and what's the quality of the output that it provides. So we have to make this choice in terms of the query plans given this spread. But not only do we have to make this choice, as I said earlier, we actually also have to run them across a hierarchy of clusters, if you would. There would be increasingly cameras are being equipped with compute on them. They would connect to some kind of a private or an on-prem cluster, say, located in a single building or so forth. And then, of course, we have more overflow compute available in the cloud. There is varying network capacities available and so forth. And video analytics has to run across this hierarchy. And not just this, we actually think the converse is true as well, which is that we believe video analytics is the killer app for driving the important trend towards intelligent edge computing. So in our problem statement, given this setup that we have and a bunch of query plans, what do we specifically want to do? We want to pick the query plan for video queries and then place these transforms that we had across this hierarchy of clusters. And note that we have to do these two jointly. Because if you pick one, just the query plans, then you might be constrained in what you can place because the camera has a limited number of compute, the private cluster's compute is limited, the network has their own constraints, and so forth. More formally, we need to decide the query plan and the placement to maximize, say, some kind of an aggregate quality across many queries. It could be an average, it could be a fairness-based aggregate, and that would be a pluggable point. And of course, each of these queries do have diverse quality requirements. For instance, something like a license plate reader for tolling, you'll have to be quite accurate in what's the output that you produce. You can't bill someone wrongly. But if you're using it for, say, intelligent transport, like where you want to count the number of cars and you want to see how, change your traffic lights based on that, it's maybe okay if you count 10 cars as 8. That's not so bad. There are varying, across the board quality requirements, and we allow for applications to set the minimum quality that they can work with. So at an overview, the solution goes as follows, where a query comes in, we run it through a profiler. The profiler outputs this resource quality graph. And then, of course, we supply that resource quality graph along with the minimum quality of this query to the scheduler that goes ahead and executes them across this hierarchy. And the challenge in the left part of the figure here is to do this efficiently, because given the number of options that are available, doing an exhaustive search would not be preferable. And for the right one is to sort of like do this joint scheduling of where we take in the quality and the placement together. So let me start with the left part of it, which is done, of course, offline. When the query comes in, you go ahead and then profile it. Of course, you run the query immediately with like a default query plan, but you go ahead and in the background and profile it. So what does the profiler actually have to do? It has to get for every single query plan, which recall is a combination of knobs and implementations, it has to get the resources that are consumed and the quality. Remember that the resources are for, of course, individual transforms as such. Quality is defined for the entire pipeline. And what we do essentially is some kind of a targeted search where we look at query plans that are more promising, and anything around that we start investigating more, and things that are not promising, we actually don't look at it at all. We ignore it. I'm not getting into the details of it, but roughly, if this is kind of what it looks like in terms of, all the query plans. Again, the x-axis is in log scale, the resource demand, the y-axis is the quality or the accuracy of the result. Then one key insight that we actually end up using is the fact that if you look at these 2 points, right, the green and the red point, the red point is strictly better than the green one on both the dimensions, in that it is of better quality and it consumes lesser resources. So we actually, if we are considering the red point as a possible query plan, we don't really have to consider the green as such. And so if you look at all these combination of these red plans, then we would get what we define as a Pareto boundary, where each of these points is Pareto optimal, and we get this Pareto boundary. And this concept of Pareto is just classical from economics as such. And this is hugely beneficial because it hugely reduces the amount of the search space that we need for the scheduling as such. And just on this point, I'll put in a small checkpoint here that we say it's the Pareto boundary. I'll later show that we would actually use like a Pareto band, if you would, just because we have to do the scheduling and the placement together. But I'll revisit this point. So now that we have the profile, the next point is to take this and schedule this thing. Remember that this is a multi-resource problem. Like for instance, if you look at this graph here, it shows the demand on both the cores or the megabits per second, depending on what we're talking about. Like for instance, the camera stream rate, these are for 2 query plans, option A and option B. And I'm putting these 2, it's just arbitrarily picked, but these query plans have the exact same accuracy of the output that they produce. So from the point of view of the application, it couldn't care which one you pick. But if you look at these 2 query plans, look at the huge variation on the camera stream rate that you produce, because you're changing the resolution, the frames per second. the detector, for instance, whether it's a DNN-based thing or a background subtractor-based thing, and so forth. So it is like a complex, compute and resource sort of a problem together. Squall is something that we systems folks actually is bread and butter for us. So what we do is that for each plan and placement pair, remember that once you take a certain plan, you still can place it, in like a variety of options. So for every plan placement pair, we calculate the fraction of the demand that it needs at each of these locations. And when I say a location, it has a compute requirement and it has network uplink requirement. Of course, we're not talking about downlink back here. It's strict uplink. Right? So essentially what we do is calculate the max or the dominant value across all these fractions. And for folks that are familiar with the big data sort of literature, this would remind you of the DRF scheme, the dominant resource fairness scheme, where it's like a similar thing that is used across to actually merge in multiple resource requirements. And the good thing about something like this is that it avoids the lopsided drain of any single resource at any location. So that for multiple queries, that's like a good way to go about computing. And once you have this resource demand, this dominant resource demand for every placement pair, then we actually do a greedy scheduling heuristic, where recall that I had said that we get this Pareto front, but what we actually do is have a small delta, which is a Pareto band of a certain width. There was the Pareto boundary. Let's take this band of a certain width, and we need this band because often it might be a case where if you take just the Pareto boundary, you might be too aggressive. You might actually not be able to find a feasible placement option at all. So what we've seen is that usually a small, a band of a small width usually suffices. And yeah, so this still reduces the search space considerably when we have to function here. So putting this together, what we've seen in our evaluation is, we evaluated this thing with video cameras that are, outdoors and indoors, from the surveillance field, from traffic. The frame rate of this thing varied a fair bit. Some of them are much more older cameras. The more recent ones, of course, on the right end of both the frame rates and the resolution. And what we could see was that, we get considerably better accuracy compared to sort of like either static policies that are used today, or if you use more classical things like I'm going to just, define fairness of resources at each of the points in the hierarchy. We can get considerably better accuracy, and note that our Pareto band option does not really, mess up much with the optimality. We're pretty close to what an optimal, plan would do in terms of the accuracy. Some details that I didn't go through is we are able to, sort of like adapt to errors in the profile as well. Note that the profiling is done on like a selected video stream that is recorded and then you profile, but in reality things might change over time. We are able to adapt to errors in it. Some of this work for folks that are actually attending the main conference, we have some of that adaptation work that would be presented. And yeah, the system actually scales to many thousands of queries as well. So this completes this part. Let's move next to, sort of like shifting gears a little bit. Here we're talking about, so far we talked about analyzing live video streams as such. How is it that you can analyze these live video streams and place those various components of the query, in this hierarchy. The next thing that we want to do is another important workload that people with cameras usually have, which is to go back on their stored video streams or video data sets and ask questions of various forms. This is work that is appearing at the upcoming OSDI in October. Yeah, of course, again, massive amounts of video are being recorded, especially if you look at enterprise sort of settings, surveillance sort of settings. I see a lot of video cameras in this, building itself, including one there, I guess. And if you look at all these video camera streams that are there, essentially we need to be able to query them. Like for instance, in the traffic videos, find me all the trucks that were there in the traffic videos yesterday. It could be the same with respect to, find me all the people that were there at the parking lot, say after a theft or an incident that happened. The point with this is that, the current advances by the vision community with CNNs, things like YOLO, ResNet, etc., means that we can actually do a good job of finding them. The problem is that it's very slow and very expensive as well, as I would show. I mean, expensive to a point where it's actually not affordable at a price point as well. And of course, what can you do to make sure that it's not slow? I mean, of course, you can analyze all the videos at ingest time. On the live video stream, as you are ingesting these streams, let me just go ahead and analyze them, run all the analytics on them. That would make the query time fast, because at query time, it would just be a simple index lookup at that point. Find me all the frames that contain this object of a certain type, great. You just look up that index, and we know how to do that fast. Of course, you can run the expensive things, store it in the database. This is all fine, but the trouble with this is that it is very costly to be able to do it, and that's the price point that we're looking at. Nearly $400 per month for a single stream. If you have to run, for instance, say, the ResNet 152, which I think a couple of years back won the award in terms of the competition on object classification. Now, that's not a price point that's really realistic for either home applications or even enterprise applications. Okay, so since this is too costly, I guess the other end of the spectrum is clearly that at ingest time do nothing, and at query time just run the whole thing. And it's also not so bad as an option if you think about it, because most of the video never gets looked at or nobody asks questions about it. They're just recorded, and after an expiry, they're deleted. So maybe this is not so bad. The trouble with this is that it takes a lot of time. For a month-long video that you have to say query, it takes 5 hours. And this 5-hour number is not something as a straw man that I'm saying. This is based on like cutting-edge work that we have just as of last year, in terms of being able to query these video sets. Despite these advances that do all the basic things we would think of, like frame sampling, downsizing the resolution, removing frames where there's no moving objects and stuff, it still takes this long. Hardly interactive. So what we want to do is enable low latency, low cost, and yet high accuracy querying over these historical video data sets. If you were to graphically visualize it, it's across the ingest cost on one axis, as I showed. There is the query latency. Of course, the better is a lower value on both of it. As I showed, an ingest heavy baseline that analyzes the whole thing at ingest time is great from the point of view of the query latency, but not so good from the point of view of the cost. And this is on a normalized axis, so that's probably like the most expensive option. The other extreme, of course, is a query heavy thing where you do everything at query time. So from a cost point of view, it's not so bad, but it takes forever. What we want to ideally be, and I'll show how we get there with a bunch of policies, is somewhere where both the cost and the latency is low. Okay, a quick little bit of a primer on CNNs, convolution neural networks. It consists of a whole bunch of a variety of layers, convolutional layers, the rectification layers, the pooling layers that take in these outputs, and then finally in the end, there are these so-called fully connected layers that take in feature vectors from the other layers and then produce outputs essentially in descending order of what it thinks a certain object is. Like in this case, in this example, looks like the fourth most probable thing it thought about that image on the left was an apple. And so, our objectives, given these CNNs and given this motivation across the query cost and the latency, is that let's provide low-cost indexing, at ingest time, and at the same time achieve high accuracy and low latency at query time, and importantly, like a good system would provide, enable some trade-off policies between these two. So let me quickly go through the low-cost ingesting in terms of how we do that. I showed you about the CNNs, and there are plenty of advances that the CNN, the vision community has made where we can compress these CNNs, we can specialize them to, sort of like specific camera streams where we know what is happening, what the size of the objects, etc. look like. And these can be substantially, often, substantially cheaper than a full-blown CNN. So we can just take, these frames, get these objects, run them, instead of running them through the expensive CNN and indexing them, we'll run them through these cheap specialized CNNs at index time. So the cost of these is often like, 1 or 2 orders of magnitude lower than an expensive CNN. The problem here is that these cheap CNNs are not for free. They also have a much lower accuracy. And like for instance, if you look at, this descending order of probability, for instance, if an object is indeed a truck and say that's what the expensive CNN says, the cheap CNN has a list that looks like that. It thinks it's a moving van, it thinks it's an airplane. That's actually something that we did get in one of the traffic videos. It thought there was an airplane in the middle of the road. It just think, it's a truck, but somewhere down the line. But what an empirical observation that we make here is that, the best result that we get from the expensive CNN is within the top K results of a cheap CNN for a reasonably small value of K. So we use this empirical observation as part of our indexing purposes, where we use the cheap CNNs, but use this point where what we want to essentially do is if recall is one of the things that we care about, which is the fraction of relevant objects that are selected. And of course, precision is the fraction of selected objects that are actually relevant if you look at sort of the false, positive, false, negative sort of the world. What we see here is that if you look at, say, the ResNet 18, right, which is the cheap CNN, this is the variant of ResNet 18 where we removed 4 more layers from it, and and we removed 6 more layers of ResNet 18 as well again. What we see is that this is kind of what the recall numbers look like for K equals 1, which is the first row of the probability list of the CNN. If I keep increasing it, of course, what we see is that the recall keeps going up to a point where it's pretty close to what we actually want for a pretty small value of K. This is kind of exactly what we end up using. 99+% recall is often sufficient in practice for a lot of things. So cheap CNNs can be used with this, sort of like with this, if you use the top K results from it. So essentially our index diagram that we had before, all it takes is, okay, we run this, the specialized CNNs. We now create this top K index. Of course, at query time, we query this top K index as such. And of course, then run the more expensive CNNs to make sure that your results are precise, and then give it back to you. This increases the load, as you would notice, on the query time now, where you have K times more classifications that you have to do. So that is the next part, which is how do you achieve high accuracy but not pay the sense of the latency, where we have to do K times more work. What we use is to get these extracted features. Recall from the CNN diagram that I showed you, the primer, where just before the fully connected layers, you get these extracted features. What we do is cluster these objects based on those feature sets. Those are typically, I think, 1024 or 2048 byte feature vectors. And it's not something that we just made up. I mean, it is sort of like an observation that has often been seen in the vision community. These extracted features often, are similar when the images do have, sufficient similarity as well. So if you were to cluster them, then that's great, because then images that look like this will all be put in one cluster. And so if I'm looking for a singer, or I don't know exactly who this person is, but if I'm looking for a singer with this person, then I don't need to run the expensive CNN at query time on all of them, just one of them, the cluster centroid specifically. So essentially all I do here is, at query time, at ingest time, I create these object clusters, take the top K results, and then so my query time job is now much more easier. And now that we have these two, not that in describing this thing so far, I made like a lot of parameters, if you would. There is the ingest CNN that you can use. I gave examples where you could remove any number of layers from a cheap CNN. There is the K value that we could use. There is the clustering thing, which is, so that as with any clustering technique, there is a clustering threshold that you would have to use. The question is there are so many parameters. So if that is the case, then how do you trade off between, the ingest cost and query latency? And these parameters are the ones that allow us to trade off between the ingest cost and query latency. So, the way the system's abstraction would be that the user would provide you the application would provide you accuracy targets that they want, specifically what's the precision that they want, what's the recall that they want. And so for each dot here represents the combination of parameters that we have. So we have this option in terms of, a policy that is at the far extreme, and optimized for the ingest cost as such, far right, optimized for the query latency as well, but at much higher cost. And what we can do is find these kind of balance points where you get the most bang for the buck, where you get improvement in one of these metrics the most at the expense of the other. The summary of results from this is, again, we used the same data set that I showed in the first part of the talk. We used, for all our experiments, recall and precision targets of 99%. And this is 99% with respect to a full-blown YOLO V3. And this is kind of what the results look like. As before, the ingest heavy is right there. No scope that I said is kind of what we use for the query optimized thing. This is recent work. It compared to a lot of the strawman techniques, it beats the pant in terms of the query latency. So it's a pretty good baseline that we have. And this is kind of where we end up being. Our work, we call it focus, which is, from $380 a month, the figure that I showed you, the ingest cost that we have comes to as low as $7 a month per stream. And the latency as well substantially drops for analyzing a month's worth of streams. And all of this, as I said, is a combination of smart CNNs, cheap ingest CNNs that we use, cluster them so that your query latency is also low. Okay. And so a lot of this work, we've both, sort of been using this vertical of traffic videos as a driving application for a lot of our systems, and and also trying to get back to them by talking to them constantly about what their problems are and so forth, and developing systems, some of which that actually could be used and deployed by them. And the thread with traffic started with the city of Bellevue having signed up to this thing called Vision Zero. For those that are not familiar, Vision Zero is an initiative that started out of Sweden, where the objective was to get pedestrian and any kind of traffic-related fatalities to zero. And to do this, I guess what they wanted to do was use the widely deployed traffic cameras, get the various kinds of counts, detect when there were near collisions, and so forth. So in terms of the video query pipeline as such, recall that in the early part of the talk we talked about how these queries could be specified as a pipeline of various transforms. It's a fairly simple pipeline, the kind of stuff that we did look at before. It's an object detector, and it gets the foreground moving objects in the space, then a classifier, specifically this one that we've specialized to the specific set of Bellevue streams, that captures what the kind of object is, and then we can get the directional counts. And since we also get the kind of objects, we can find when there was like a near collision between, say, a bicycle and a vehicle. So finally, let me leave you with this video that shows like kind of, it's like a recent PR video that we made on the work here. The
City of Bellevue is a high-performance organization. We're constantly looking for innovative ways to advance projects that will result in a more efficient and safer street system.
The City of Bellevue was working towards this program called Vision Zero. The goal of that program was to get to a point where there was zero traffic-related fatalities.
Microsoft reached out to us and inquired about leveraging our existing camera system to derive insights on how people move around our city and to address a major safety concern, road collisions.
Traffic-related deaths are among the top 10 reasons for fatalities worldwide. So we thought this was a project that has a great technical potential and a huge social impact.
The way they would do it is they would manually send people to intersections and count how many things were happening. Now, this is not a scalable solution. It requires a lot of money, it requires a lot of time. With computers, we are able to do this much faster, it's very accurate, it's low cost.
Live video analytics is the technology that analyzes video at the real time that provides insights and help them make decisions and validate decisions.
It takes each of the frames of the video and it detects all the objects that are present. It sees what the direction of these cars is and increases the appropriate counts for these various directions.
Our team started looking at computer vision about a year ago and have been making the service itself more robust, making it more configurable so we can support additional scenarios in additional cities, and then driving the cost down. A lot of what we've done is figuring out how do we connect into the existing workflow that the city uses. The more we can feed our new data into their existing tool set, the easier it is for them to take advantage of it.
What's really exciting about the partnership that we're developing with Microsoft is the opportunity to leverage cloud computing, machine learning, and other technologies to drive insights on those close call situations of cars abruptly stopping or swerving, and then to engage proactively in a corrective measure.
Compared to the technology that's currently being deployed by many cities, I see video analytics providing a dramatic shift.
Customers around the world all welcome the idea and they all share the same type of business needs with us. So we do have true belief that this has global application.
Video analytics has created an opportunity to be able to do something that can potentially save lives and people are willing to deploy everywhere. I can see this being used with smart cars or self-driving cars. We have opened up people's eyes of the possibilities. That's what we are after.
Okay, so I guess to conclude, I hope through this the sample of the work that we have done on live video analytics as well as stored video analytics, I hope I've convinced you that this is quietly a problem that's in the systems and networking domain, and there are plenty more remaining to be done, from the point of view of the edge-based, analytics, sort of like cross-camera analytics and so forth. And yeah, if you want more details, please feel free to check out any of those two URLs right at the bottom. Thank you.
Thanks, Ganesh. Very nice talk. Any questions?
Yes. I think.
Okay. I have two questions. So the first one is, in the first part of your talk, you mentioned about the plan and location pair. So what does the location actually means in that context?
So location means, like, for instance, say you have these 4 components, right? An example of a location would be to say that I would place the decoder, say, on the camera. Maybe I would place the object detector on the camera as well, the tracker on this private cluster, and then the final outputs of the tracker, I would send it to the cloud for further processing. This is an example of a placement, and for a specific plan as well. So now we have this combinatorial option of plans and placements. That was kind of what the point.
Thanks. And the second question is that about the Vision Zero. So you apply the live video analytics into the this plan. So I mean this I'm not sure what's the ongoing the current progress of this plan. So, but I'm not sure if you analyze some kind of potential dangers. So, what can you take action to prevent the fatalities?
True. What is, broadly speaking, what does the city do with something like this, right? Yes. So the city, you know, is in this video, you must have, if people that did notice, it was this thing called alerts that we show once in a while. Alerts, for instance, is that says that the amount of traffic is either abnormally high or abnormally low. Now that helps them actually deal with it much more targeted, because a single person doesn't have to look at all the video streams. So then it helps them, say, dispatch personnel to a specific, you know, point and so forth. Since we have directional counts as well, it helps them set the traffic light durations in a way such that if there is a known set of congestion in a specific direction, for instance, say a left that's not protected, let me increase it to make it a protected left or so forth. From the point of view of a safety thing, yes, they can put up signs, you know, that say that, you know, watch out for an oncoming pedestrian or a thing, or even things like the fact that, okay, you know, something that was like a free stop and go, let's actually put a real red light so that people cannot go, because there are just too many incidences of near misses. So a whole bunch of proactive and reactive measures that they could take based on the data that they have.
Thanks.
Any other question? Yes.
Yeah, thank you for the talk. Just a quick question for the second topic. I understood that the problem was the ingestion cost. So as I got that, you meant the storage cost, right? But before and after the optimization that you applied, you have the same amount of data that you store, right? Because you still need to throw the same data through the expensive CNN. So where do you save the cost here?
Right. So the problem was not on the storage cost, but sort of like the compute cost that you pay for while you ingest the videos. And this is not the storage per se, but say I'm running some kind of an expensive CNN on the video streams as they come in, then I have to provision for that much resources, say in the cloud or something. So that compute cost for the video analytics is what we save on. Your point is spot on that the amount of video that we store is the same before and after. That's not what we're saving on. Yeah, but typically the storage is not the pain point anyway. It's the provisioning of the VMs for the compute that's the pain point.
So also I have a question. Regarding the first part of your talk, you were solving a scheduling problem, right? You were assuming infinite resources, or at some point you may run out of resources in any of the placement where you can place things and so on. And eventually what happens if you have to redo the scheduling because you are not anymore in a position to accept new jobs or new requests and so on? Will you redo everything or do some incremental updates? You thought about this?
Sure. So two parts to the question. First one is we don't you know, assume infinite resources, but we do assume that there is sufficient resources to get the minimum quality that everybody is asking for. Now, of course, there is a utility thing where if you provide me something more than the minimum, I am that much more happy. So given that as the resource requirements, then how do you solve the scheduling problem is the first one. Your second point, yes, we do adapt over time. You know, queries keep coming and going. You know, as I said, you know, that's upcoming at SIGCOMM, you know, the query plans that is the best keep changing over time. So at this point, we don't do anything incrementally. You know, we just run the whole scheduling thing again. Given that it is not that expensive to run, we run the whole thing again. I am sure there's possibilities for doing incremental scheduling algorithm stuff.
Okay. And regarding the second part, you mentioned there are two key factors that save on cost. One is to use the simpler neural network to do the first part of the classification, and then also to store and send and process the features already extracted from the first CNN.
cluster.
Right. So which of the two is provided the more gain. Because to my understanding, training a deep network is much more expensive than training a small, not deep network. But once you have trained it, there is not much difference if you have 7 layers or 6 layers or 2 layers, right? The most of the cost is on the training, not on the classification part. So my understanding would be that the majority of the benefit comes from the second key idea to just leverage the features as extracted by the first layer, right?
Right, that's a good observation. I didn't go into it in detail. That's right, that most of the cost that we save, that comes from using the cheap CNN. Most of the using this clustering of the features, that saves primarily on the latency that we get. That's not particularly saving on the cost as such. So that's kind of, you know, but if you look at it, again, the cheap CNN is the one that affects the recall as such. And this clustering affects the precision as such. So yes, there is like a separation of duties and responsibilities between these techniques.
Any other question? Okay, so thanks, Ganesh, very much again for your nice talk. We now have 3 talks, actually all of them using neural network and deep learning. So the first talk will be given by Christian Lumezzanu. He's a senior researcher at NEC Labs in Princeton, where he's working on networking and machine learning, application of machine learning to the networking field. And here he's presenting a work on deep learning and neural networks for network analysis. And his work is done in collaboration also with Ming-Da Li from UCLA, Bo Zong, and Ai-Fen Chen from NEC.
Can everybody hear me? Yes. So this is work that started as a summer internship at NEC Labs. Ming-Da Li, the student, is from UCLA. And so he started this work last summer. He's been working on it ever since. We have a bunch of work done after this paper. So ask me afterwards if you're interested. So this is about how we learn representations, vector representations of IP addresses. So IP addresses, when you think about it, they're everywhere. So every device that connects to the internet needs an IP address. But when you look at an IP address like the ones on this slide, they don't really mean much unless maybe you're working for the company that owns them or you're working in the area. So what people have done over the years, they have created artificial mappings between IP address and humanly readable objects. Like the more famous one is that they associate IP addresses with names. So anybody can do a whois lookup and find out who's the organization that owns a specific IP address. Another example of such mapping are the IP blacklists. So if you want to find out malicious IP addresses, you go to the IP blacklist and you see whether that IP address has been used in the past to send malicious traffic. Yet other types of such mappings are geolocation databases that map IP addresses to locations on the globe, to physical locations on the globe. And so the common theme across all of these mappings is that they're effectively functions. So they map one IP address to a human readable object, like a name or a binary label or a location on the globe. And they are all started by humans. And most of them are artificially created by humans. So this is all good. They have been immensely helpful so far, but the question is sometimes they're outdated, sometimes they're not updated in time, sometimes they're wrong. So there's a very small opportunity here. And the question that we started when we started this project is, can we learn anything from IP addresses automatically? So by taking the human as much as possible, taking the human out of the equation as much as possible. And So what we wanted is to have the IP address and try to see, is there anything we can learn from it? So as an analogy, think about it the way we learn from an image, and this is pervasive these days. So we have an image, we take it and represent it as a series of bits, and then there are algorithms that analyze these bits and identify features, and then they can tell us whether that image contains a dog or a cat or a smiley face. And in a similar way, what we want is we take an IP address, we represent it as a series of bits, and then there's an algorithm that tells us whether that IP address is malicious or whether it's located in Hungary or whatnot. So this is the overarching goal of our project. So we haven't solved this in this paper because it's pretty difficult, to be honest. But what we wanted to start with is something that's a little bit more tangible. So we wanted to maybe see, so this is a problem that has been looked at before in the research community. And we wanted to see if we can learn vector representations, or some might call them embeddings of IP addresses, that preserve structural properties of the internet. And I'm going to explain what each line on this slide means in the next few slides. So first of all, we want to learn something. We want to learn a function, a mapping between A and B. So in this case, A and B are, A is the IP address, so IP address space. Like think about all the IP addresses that could exist and in the internet. And then when I map IP address, as I mentioned, to a high dimensional representation space. And this could be any dimensions. That in this case, I just put in D equals 3, so 3 dimensions, just to show it easier on the map. But you could imagine that D could be as high or as low as possible. So we call these vectors, we also call them embeddings. So now, what are the properties? So we want to learn a mapping between IP and this high dimensional space, but what properties should this mapping be to preserve structural indeed? So structure could be defined in many ways, and could be maybe preserve connectivity between routers, or the order of routers on a path, or neighborhood of a node. So in this case, we looked at two simple definitions of structure. One of them, we wanted to preserve local structure in the internet. So this means that if we have 2 IP addresses, like the ones, say, they start with 138, that are close together in the IP space, like they're maybe part of the same organization and they belong to computers that are 10 meters from each other, their vector representations should be also close to each other in the embedding space. That's number one. Number two, we wanted to preserve some notion of global structure. And we looked at a simple distance metric, like the hop count between any 2 IP addresses. So we wanted to say if 2 IP addresses have a certain hop count between them, like the number of routers on the path between them, we want to preserve as much as possible that hop count in this embedding space. So that's how we started. But so then it came the question that, so for images, and I made the analogies with images, for images it seems simple because we have an image and it's clear we can identify features that make that image, that can tell us that that image contains a smiley face, but we don't know what features to identify in the bits of an IP address. So the bigger question that is there any notion of structure encoded in the bits of an IP address? And luckily, we know that there is structure in the internet. We know that the internet is structured. We know that IP addresses are not assigned at random. They're assigned based on a certain scheme. And we know that there are routers in the internet that can know how to read IP addresses. That's how routing works. So our routers look at the bits of an IP address and they can tell whether this packet should take this interface or this other interface towards the final destination. So then we started by making 3 observations about the IP addresses and the IP space that would later help us build a neural network to learn from IP addresses. So first observation is that, so each IP address, it's associated with a number, which is called the routable prefix, which in some sense, it breaks that IP address into it. It splits it into the network part of the IP address and the host part of the IP address. And in some sense, you can think about it as it creates a 2-level hierarchy where the first part, the network number, identifies the big network to which that host belongs, and then the host part identifies the host in that network. And so the the network part is a little bit more important in identifying the specific location for an IP address. So now, because this routable prefix changes from IP address to IP address, so it's not the same number every time. So we wanted to normalize this an IP address. So we gave four bytes for the network part, 4 bytes for the host part. So we made everything 8 bytes. So that was one observation. So there's some notion of structure already encoded in the IP address. Second observation was that, so similarity equals proximity in the IP space. So what does this mean? So what we did, we looked at some data, and I'm going to describe the data a little bit later. So we looked at pairs of IPs that share the same byte only, the same 2 bytes only, the same 3 bytes only. And this is not surprising at all. We find out that the more similar two IPs are, the closer they are. So this kind of told us that we want to, it's a good thing that we want to keep the representation similar for similar IPs. And final observation is that in an IP address, context matters. So think about natural language processing and think about when we want to translate something. So you have here two sentences in the English language in which the word right is a homonym. It means a different thing depending on the context. And so this is very important when we do translation. So when I run these two sentences through Google Translate for Hungarian, it gives me totally different words, nothing to do with so the word right doesn't replicate itself in the translation. So then it's the same thing with IP addresses. So if you look at the second byte there, 254, that byte may indicate something different depending on what's around it, right? What's the first byte of the IP address. So what this means is that context matters, and we have to take into account context to get the final representation. So this is it. Those are the 3 observations. And based on this, we devised a 10-layer neural network. And what this neural network does, on the input, you look on the lower part of the slide, it takes in IP addresses and real hop counts between some of the IP addresses. So B0, B7 are the bytes in that normalized IP address. I told you we normalize the IP address and we make it on 8 bytes. So now what we do, we don't feed the entire IP address all at once. So for the first 8 layers, at each layer in particular, we feed 1 byte of the IP address. So that means that the leftmost bytes are more important. They traverse, they go through more of the network. So they have a chance of influencing the representation more than the rightmost bytes. So in this case, the first 8 layers compute the representation. The last 2 layers, we take 2 representations, we compute distances between them, compare the cost, and then backpropagate to update the weights. But let me just zoom in a little bit and tell you what's going on at each layer or each section of the network. So this is, like, any of these, the first 8 layers are the same. So this is how one layer is. We have the IP address, a specific byte of the IP address coming in from the bottom, and we concatenate this byte with the output of the previous layer. We do a linear transformation with the weights and biases of the current layer, and then apply the soft sign function to just squash it between -1 and 1. The output goes into the next layer, and so on until we finish all the bytes, and then we come up with the current representation. We take 2 representations, we just run a simple Euclidean function between them and compare it with the real distance if that real distance is available. We have a cost based on this. We want to minimize this cost. So based on, we apply an optimization that backpropagates and updates the weights so that after a certain number of iterations, which is we can set at the beginning, it ends. So just to give you a quick example of what this means is that imagine we have 6 IP addresses from A, B, C, D, E, F. And we don't have a complete all-to-all information about distances between them. So that matrix distance may be very sparse. So we take all the information we have, including IP address values. we build a model, we train the model, and based on this model, we can compute representations for all IP addresses in the original training set. Based on this representation, we can estimate distances between them by just simply computing Euclidean distance. So let me show you some results. So we are using some publicly available data, and this is data that was originally collected by KDA through the ARC project. So they maintain a set of monitors around the world that try to ping at regular intervals an IP from every prefix in the internet. So the data that we obtained had around 100,000 information about 100,000 IPs, the routable prefixes, and hop count information to about 90 ARC monitors. But this information, so if you think about the matrix, 100,000 by 90, wasn't complete, was far from complete. Actually, it's only 15% complete. So we don't have distances from all IPs to all monitors. And so one initial result that we got is that, so after we trained for around 3,000 iterations, we get an absolute prediction error of the distance about two hops. And this was, we compared it with a mean-based approach. And this wasn't a simple mean-based approach. We looked at every one of those 90 monitors and every IP that could connect to those monitors and computed the mean according for each monitor in itself. So it was about a one hop improvement, or around 30% improvement. But I think an even better result that underlies the power of this method was that we could learn representations of new IP. So consider the example before where we embed in 2 dimensions. And we have that the initial IPs, we create a model, we train a model for them. And the advantage of this model is that even if we have new IPs like G and H that were not seen by the training, were not used at all in the training, we don't have any information about any distance to them from any vantage point, then we can still compute we can run them through our model and compute vector representations for them that allow us to estimate pretty accurately the distance, the hop count distance to them. So just to show you the results, so this is the distribution of the hop count error for the known IPs. You can think about it as the training error. And then once we obtain the model, we ran a bunch of new IPs, not ever seen before, and this is the error of the new IP. So it's not that much worse from the training model. And again, this is without any information, without any distance to these known IPs. The only information we have about them is just their IP address value and the routable prefix of that IP address. So there are more results in the paper. I encourage you to go look at them. As a summary, this is that we're trying to use a deep learning and that takes into account structural properties of the internet to create an automatic mapping from IP addresses to a high-dimensional embedding space that reflects these structural properties. And what we're doing right now, I mentioned this is just the first step of the project, is that I mentioned at the beginning that people are creating these artificial mappings, IP blacklists or geolocation database. We want to understand whether we can create these mappings automatically. So essentially, can we learn a function that could detect malicious traffic or malicious IPs? Or can we learn a function that could automatically detect the location of a certain IP? And this is the end of my talk. Thank you very much.
Thanks for the talk. This work reminds me of a recent pastor work in our group. Please go back to the previous page, the ongoing work. Okay, the ongoing work.
This one?
No, next, the ongoing work. Yeah. So for the first ongoing work, how to detect malicious traffic on IPs. In fact, in my group has conducted a similar work. We want to detect we want to recognize the type of traffic based on the payload So we also use the analogy. We analogize the payload into the graph, and then we want to use some deep learning method to classify these images. Then we can deduce whether this traffic is which traffic belongs to which class of protocol. But later, but finally, this work becomes a failure. The reason is because the traffic is encrypted. That means the features are hashed, and it becomes completely random. So let's turn back to this work. If I want to detect the malicious traffic with IP, for example, if we know the IP and then we want to detect the traffic with the IP is good or bad, then if the attacker has some proxy servers, for example, his original IP is hidden, but the malicious things are conducted by the proxy IP, and then the proxy IP can change all the time. Then even you got the data, they are also completely random. You can't say, oh, this IP is good and or that IP is bad. So I doubt the feasibility of the first work. And as for the second work, how to detect IP location.
So actually, can I stop you there?
Okay.
Actually, we can say, because the work that we're doing is we're looking at spoofing. We're trying to detect spoofing, which is exactly that. We can say whether this IP is the good IP or whether this IP is spoofed. And actually, I have some results. We can talk offline because it's more to explain that actually show that we can detect spoofing with some level of accuracy.
You mean you can detect the original IP held by the attacker?
Yes.
But then there comes...
And we were just looking at the IP. We're not looking at the payload at all. We're just looking at the TTL field, I'm sorry. So that's one field in the payload.
Then there is another problem. If the proxy IP is good, it is because we know attackers usually use some proxy IP. They may first control some IPs from the victims, and then they use the IPs to make some bad things. So if I'm the victim, my computer, my server is controlled, and my IP is controlled, then we
cannot detect the victim where the victim is. We can detect the IP is controlled by somebody else.
Yeah. Oh, okay. In that way, that even I'm the victim, you also think this IP is bad.
Yes.
Right? Okay. And for the second work, detect the IP location. I'm not.
This is just that we have for the first one we have actually done some work, and we can even talk online. For the second one we haven't done any work, so it's all in the level of discussion and ideas.
I just want to share my opinions with the second work about its motivation. What is the practical scenario with the second work? What can I do if I know how close the IP is? If I want to use some public cloud service, I just purchase the IPs, and then if the cloud providers guarantee that the service quality, for example, such as the bandwidth, such as
I understand the question. Let me answer. So, for example, a practical scenario would be in censorship detection. So, sometimes you want your traffic to not go through a certain country, or you want to ensure that it goes through a certain country. So you can say you can verify whether that IP is based on that country or not. That's based on geography and geolocation.
We have time for another question.
So thank you for the talk. It's actually quite cool. I'm thinking of this as IP to VAC, like sort of word to VAC.
We did too. Yeah, I didn't want to mention it because we don't have any results on it, but we're thinking along that direction, like word to VAC, yes.
So in word to VAC, there's a reason, at least there's a hand-waving argument that says why there's semantic content in the vector, because you're looking at the words that are nearby this word, and so words that have similar meaning are probably in similar contexts. For the distances, the hop count thing, you don't know the underlying topology. Do you have a reason why you're getting a reasonable accuracy even though you don't? I mean, here's these two pairs that are not, you don't have a hop count for, but you're estimating with reasonable accuracy what it is. So do you have a...
I think I can speculate that it's the division into, we feed each byte in turn, so we don't feed all the bytes all at once. So the byte, each of the 8 bytes is a reasonable separation. I don't think it's the best one, so we're actually looking into how to find better delimitations. Like there's some work about entropy and IP, and they're trying to look at conditional probabilities between bits in an IP address. So we're trying to look at that and essentially identify semantic groups inside an IP address and try to see whether by feeding a semantic group rather than a byte would give us better results. But again, we're thinking about it, doing it. I think we have done a little bit of it, but I don't have any results. So I cannot tell you whether it would work or not. Yeah, we thought about, we didn't do anything on it, yeah. But it would be a good follow-up, yes.
Okay, we are running out of time, so let's thank the speaker again for a nice talk.
Thank you.
And our next speaker, Fabian Geyer, right?
Yes.
He's a postdoc researcher at TU Munich. He's working on machine learning for computer networks, high performance packet processing and performance evaluation and modeling. And he's going to present here his work on learning and generating distributed routing protocols using deep learning.
Okay, thank you for the introduction. So this is a work which looks at how to generate computer network protocols using graph neural networks. Oops. Okay, so if you look at network protocols nowadays, usually they are manually developed, they are manually engineered, and also if you want to optimize them, everything is done more or less by hand, by engineers, by committees like IEEE, IETF, and so on. If you want to optimize them for a specific use case, it's quite hard sometimes. Like for instance, if you want to have OSPF weights and so on, it's quite difficult sometimes to find the good parameters in order to make it work in a performant way. And the protocols are also sometimes slow to evolve, and they are not always fitted to the use case they are targeting. Like for instance, if you look at mobile network, sensor network, those have other requirements in terms of energy, in terms of like how much time they can spend to send data on the network and so on. So the question I asked and I try to solve in the paper I present is, can we automate distributed network protocol design using only like high-level goals and data? And if the answer is yes, can we also incorporate some specific properties, like for instance, resilience to fault? Like if you have a packet loss, the protocol still have to be able to recover from this. And the contribution I will show now is a method for generating network protocols using so-called graph neural network. I have an introduction about this later. And my focus for today, since there are lots of distributed network protocol that we could train for, is routing protocol. So one question one might ask is, why now? So is it a good time now to do this kind of research or not? And I argue that it's actually quite a good time to do this kind of research. If you look at two recent trends in networking, we see, for example, more and more research for in-network processing, more and more resources for doing this. You have things like SDN, P4, DPDK, always more flexibility in the network, always more computing capabilities in the network, meaning you can actually do something more complex with your switches, with your routers, and so on. And you see new paradigms in networking, like for instance, data-driven network, data-driven protocols, and so on. So if you look at the workshops from this year's SIGCOMM, you have 3 or 4 workshops which kind of focus on this. So I think it's quite a good time to do this kind of research. And also from a more general view, so if you look at the field of artificial intelligence, they are also publishing more and more on this kind of bigger research question, which is how to design autonomous agents which communicate and collaborate to reach a common goal. Here on the slide, I have 2 examples of what's happening in other areas of artificial intelligence. So the first one is DeepMind, for example, who focuses at the moment, after AlphaGo, they try to do multiplayer game. One of them is Quake 3, where they want to have 2 agents fighting against 2 humans and see who wins. And at the moment, the machine is winning, so we see it's a good direction. And another recent result is OpenAI, which also does this autonomous agent trying to reach a common goal with Dota 2. So those are quite new. Okay, so now the outline of the remaining of my talk. So introduction first, I will show you what kind of assumption I take for the routing protocol I'm trying to generate. Then I will explain you the machine learning part, so those graph neural network, then an evaluation on a data set, and conclusion. So what kind of, what am I speaking about when I say distributed network protocol? So in MIME, you can abstract most of the network protocol with those 2 points. So you have distributed node, which kind of needs to solve a common high-level goal. And in order to reach this goal, they need to somehow exchange some information. Like for instance, the topology of the network, they need to learn it and then use this to route packet on the network. You have also other examples like congestion control. You have different nodes which need to adapt more or less the bandwidth in order to not overload the network. And here you have also other examples like load balancing, content distribution, and so on. So for this talk, I will mainly focus on the first example, which is routing, and you can keep in your mind this example. So I try to target a really simplified version of OSPF. Okay, so what kind of requirement do I have for my protocol? The routing needs to follow some well-known and predetermined pathfinding scheme, like for example, shortest path routing. The protocol needs to support dynamic network. So if you have nodes which leave the network or enter the network, it needs to support this and adapt the information it sends to all the nodes in the network. One target is to be resilient to packet loss, and it should work on any kind of topology. The assumptions I take is that router first start with 0 information about the network topology, and using the information the router are exchanging, they will learn about the topology, how it looks like, and what kind of routing they will use. Okay, so the general idea, so this is more or less the concept. So first you represent your network as a graph. So here below you have your network with some routers, and you represent it as a graph. So you have the nodes in the graph, which represent routers. Edges in the graph represent your links, and the data which is exchanged between the node in the graph, it corresponds to the communication between the nodes. Then you pass this graph to a neural network, which is able to process graph. This is called graph neural network. And then the final step is to train this neural network to be able to emulate the network protocol's goals that you have in mind. Okay, so since not all of you might know what actually graph neural networks are, I will introduce here the main concept. So it's concept which has been introduced about 10 years ago. And it's a special kind of neural network which is able to process graph. So usually the kind of neural network we see in lots of papers, they are able to process either one-dimensional signals like audio or two-dimensional data like images. And here for this, it's a bit more special. We want to analyze graphs. So it's not exactly 1D or 2D, it's a bit different. So here on the right-hand side of the slide, I have an example graph, which I will explain the different steps of the algorithms on. So pay also attention to the graph, it will change through the slide. Okay, so the principle is that you initialize first all your nodes with a vector, which is a real vector, a real value. Each node or each vector is computed according to the neighboring value. So for instance, here for node 2, this vector is a function of the other nodes. But since we have, like, for 1, it depends on 2, and 2 depends on 1, we have kind of fixed points. So it's throughout the graph. And we see here, so each vector is a function of the set of neighbors. How do you implement this? So you use fixed point iteration. So it's represented here. I initialize each node here. I represent it with a different color at time t equals 0. And then at each iteration, you pass the different information through the graph. So we see here for t equal 1, we have some information which has been passed. Like for instance here, the node 1 has gained one color from node 2. Node 2 has gained 3 other colors from its neighbors, and so on. And you iterate like this. So at time 2, again, you iterate until you have reached convergence. So here at time 3, all the information on all the colors have been passed through the graph. And you finally use a final function called here g to make a prediction about the nodes. So that's the main concept. Now about implementation. So the functions that I showed you before, f and g, they are a neural network, like standard neural network, feed-forward neural network. They can be implemented in the paper from last decade, they have been implemented using standard feed-forward neural network, but you can also implement it using recurrent neural network. So this is in a more recent paper from 2 years ago. And you can also learn some special values for the edges. Like for instance, a paper from this year, you can learn actually which edges are important in the graph. Here is a small representation about this architecture. So you initialize the vectors with the input values of the node. You circulate those information in the graph using A here, the adjacency matrix of the graph, until you reach a final iteration here with big T. And finally, you make the final prediction using a standard feed-forward neural network. And the main advantage of this architecture is that it's not restricted to any specific graph. So you can analyze any graph sizes, any graph like shape, and so on. So it means also you can analyze any kind of network topology that you want. So now that's the concept, now back to computer networks. So we have seen here on the left-hand side, we had node which exchanges some vectors on some edges. And if you translate this to computer network, you have routers which exchange also data. In this case, it's not anymore like real value, it's packets. And through different iterations, you can pass data inside your network. Here is a small algorithm that you can implement to do this. So the nodes in your computer network, they periodically broadcast a hidden representation vector. And they also process in a second step locally the received information from the other nodes and apply simply the function f, which has been previously trained. So you first train it here on your graph, then the f function and the g function that you've learned from before, you do this locally on each node, and then you repeat this periodically. Okay, so now more about the details about actually how you implement or how do you encode the data. So the main goal is of the routing protocol, of any routing protocol. So given a destination, IP address, for example, or router ID, you want to know, in fact, which interface of the router you need to use. And that's how you, kind of the goal I want to achieve. So here I have a detail about actually how do you transform a network topology to a graph. So each node or each router in the computer network is a node in the graph. Same for each interface of the router. So here, for example, the router here, we have two interfaces, which are those two nodes here. The other two routers here have only one interface, so it's only one node. And the output feature of each node, so for the routing routers, we have no output features since we are not interested in the output features. But for the interfaces, basically given a destination, I want to know the interface I need to use. For instance, for this router, since it has only one node, so when it wants to send a packet from here to here, we need to use this interface. So we know this is active. Same here, so for the router here, it has the choice between two interfaces to reach the destination here. But if you use like simple shortest path routing, you know it's this node which needs to be used and not this one. So that's more or less how you encode your routing protocol. And finally, yes, I forgot this point. So the edges on the graph correspond simply to the physical links. Okay, so now a bit more detail about the neural network architecture. So the information which is exchanged between the nodes in the topology are those hidden vector. And after a while, they simply represent the routing table. And each time you want to send a packet to a given destination, you need to query the routing table to know which interface to use. So that's why I split my neural network architecture into two parts here. So first, you have the distributed message passing here, where it corresponds to the packet which are sent on the network. And finally, after some iteration, it's saved locally. You don't send any information anymore on the network. And each time you want to reach a specific, or you want to know which interface to use given a destination, you query the hidden representation using like a special query vector. So you do simply a multiplication. Then you apply the final step of your neural network, and you know which interface to use to send the packet. Okay, so now enough for the technical details. Now we have a look at the numerical evaluation. So for the data set, it's based on the topology zoo. So that's the website of the topology zoo. It's a website containing about 200, 250 different network topologies which have been found on the Israel network found in ISPs, for example. So I limited for my data set to relatively small networks, so a maximum hop count of 10 and maximum number of nodes of 20. And this limits to about 100 topologies, so I extend those topologies by simply adding and removing routers randomly in those topologies. I also randomly generate router identifiers, so it means in total I have more or less 40,000 different data points. regarding the use case, so what kind of goal the routing protocols need to achieve, I have two use cases. First, shortest path routing, and in the second point, max-min routing. There are some details about this in the paper. So first, accuracy. So we see here the two use cases. First part of the plot here, cold start, it's when the network is booted for the first time, and then on the right-hand side, warm start, that's when the nodes have been already running for some time, and then you add or remove simply a router on the network, and you see if it changes or not. And in average, the routing protocol is able to reach quite good accuracies, so up to 98% for shorted path, 95% for max-min routing. Then you can have a look also at how the accuracy of the algorithm changes over time. So for traditional routing protocol, it's also sometimes called convergence time. And you can see here, after some iteration, the accuracy grows always. So that's more or less after you have propagated more and more information in the network, after the nodes have learned more about the network topology, the accuracy increases. So that's more or less what you can see on both cases, both for cold start and warm start. Then, as said in the beginning, the network should also be able to, or the protocol should be resilient to packet loss, and you can actually train it specifically to do this using dropout layers. So we see here at the top, when I don't train the neural network explicitly to support packet loss, we see that as the x-axis is the packet loss probability, we see that it decreases quite sharply for both kind of routing protocol, while if I specifically train my network protocol to support routing, to support packet loss, we see that the accuracy kind of stays at a nice level, about 90%. Okay, I will jump this for time, and now conclusion. So what I showed you today is how to generate distributed routing protocol using graph neural networks. The key idea is to represent network topologies as graph and then train specifically some properties of the protocol using graph neural network. The key lesson that I learned during this work was that graph neural network are really well suited to reason about computer network. I have also other papers where I have applied this to predict bandwidth of protocols and latencies of protocol. And in future work, what I would like to look at is compare those kind of learned protocol against manually engineered protocol, and also look at other use cases, so other distributed protocol. So thank you for your attention.
We have time for a couple of questions.
It is very nice talk, and my question is that because the neutral network can always has some errors, such as it cannot ensure 100% accurate. So there's maybe some possibilities that this destination cannot be reached. Have you considered that cases?
Yes, so didn't look into detail into this, but for future work, I have to look at this, that's for sure.
Okay, so in your experiments, have you found that some case that certain pair of certain destinations cannot be reached?
No, I mean in the data set I create, I explicitly have a destination that can always be reached. That's for sure. When I generate the data sets, but I can also generate other data sets where some destination cannot be reached, and that would be relevant.
Okay, thank you.
Thanks for the talk. So in your model, you use a gated recurrent unit. So what's the effect of these units?
You mean the GRU?
Yeah, the GRU.
Yes, so the main case, so in the original paper, so the paper from 2009, yes, 2009, in fact, they do this fixed loop iteration. They do it for an unlimited number of time, so unlimited number of iteration, which is not really good, in fact. So what has been proposed here in 2016 is to loop only for a fixed number of iteration, and that's why they use the gated recurrent unit. So that's more or less the justification of why use this. So I recommend you simply look at the paper here. It's also cited in the paper, and they explain exactly why it's better to use a recurrent neural network.
Thanks.
Hi, thanks for the talk. Quick question, the adjacent matrix and the topology, is it fixed or it can change over time? I didn't.
It can change over time. So it's shown in the plots. So I have a first part which is completely cold. So the network is booted, and then the warm part, it means the network has been changed. So someone enters the network or leaves the network. That's why I had two plots each time.
So I also have a question. It seems to me that you are trying to solve a problem for which you know the optimal solution already, like shortest path or
yes.
Whatever. What will be the advantage of using this instead of using the optimal solution that you can get? Or if you like, what will be your next step
yes.
After this?
So in order to solve the optimization problem, you need to have a global view of the network. So you need to know more or less completely the topology. But here with the protocol I generate, I need to exchange somehow information on the network, and I don't know in advance what kind of information I want to exchange. It's like in OSPF, you have those tables which are exchanged between routers. It needs to be exchanged because the computation is local and not global.
But if you think about distance vectors solutions, then
yes,
you solve the same problem, right?
Exactly. But the idea would be to generate more complex protocol at the end. So here that's one example, but in the future we will need something a bit more.
So include some performance metrics that will be hard to code in a
yes, exactly.
Okay, nice. Okay, thanks. Okay, no more questions? Okay, so let's thank the speaker again. And the last talk for today, okay, Albert Mestres, right? From Barcelona, Technical University of Catalonia. He actually graduated last year from l'Università Politecnica di Catalunya. And he is now postdoc at the Technical University of Catalonia, where he's working on networking, machine learning, and nanotechnology problems. And he's going to talk about neural network and delays.
Thanks for the presentation. Yeah. Well, I'm going to start the presentation talking about the knowledge-defined networking paradigm. And then I will focus on the paper. I will start with the use case presentation, the problem statement, the methodology we follow in these experiments, some results, and finally the conclusions. So nowadays, machine learning is being applied in the networking field, but this is somehow new from 2 years ago. But the idea of applying machine learning in this field is not new. In 2003, Clark had the idea of modeling or using machine learning in the networking, but we were not there, maybe for two reasons. Machine learning tools nowadays are much more advanced than before, and the network has also changed. The SDN paradigm has provided tools to apply machine learning. For example, We have a full control of the network using the SDN control, and also a full view of the network, thanks to the network analytics platforms. And this trend is not new in the networking field, also in the mobile sector and the automotive sector. We are moving to the software and then to artificial intelligence tools. So this is what we call KDN, knowledge-defined networking. So this is the operational loop, and the analytic platforms recover information from the network, the forwarding elements, and from the controller. And then we can build ML models using this data. And these models can be used to control the network, either by the network controller, operator, which can use these models to take some decisions, or by automatic decision tools to control and take decisions to the SDN controller. And this has many applications. So the more important applications are resource management, performance optimization, and the final objective of KDN is to go towards self-driving networks or autonomous networks. And the architecture of the KDN is adding the knowledge plane on the top of the SDN architecture, in which we have the data plane, the control plane, and the management plane in the back. So the KDN has many use cases. In this paper, we focus on black box network modeling in order to optimize the network routing, but there are many other use cases, such as modeling of NFV elements, automatic knowledge extraction from network logs, or also in 5G networks, or planning networks in the long term. So focusing on this use case, we plan to automatically route the traffic in our network. For example, if we have two big flows, the green and the red flows on the left, but if the green flow disappears and appears this new flow, it may be interesting to reroute the red flow to another path to avoid congestion in this path. So for this, we are having a model of the network could help to improve the routing of in the network. If we have a model that knowing the configuration and the traffic of the network, we can predict the performance. We can use a classic optimizer to find the optimal configuration of the network when the traffic changes, and to apply the configuration in the network to optimize the performance of the network. So the main question we want to answer in this paper is if it's possible to model the performance of the network using a black box model approach using machine learning. So in the bottom layer, we have the network. We model it as a black box, as a deterministic system with memory. But as an input, we take the traffic. The traffic is a stochastic process. In this paper, we consider only the mean, and the output of the system is the delay, which is also a stochastic process. And we also model it as only with the mean of the delay. And these are the input and the output of the neural network that we have. So the function we ideally want to have is knowing the traffic and the configuration, what is the performance of the model. But in this paper, we simplify the problem, and we try to model the delay of the network only as a function of the traffic. So what are the other approaches to model the network delay? Usually, simulator has been used to model the delay, but the simulators are usually, they have high hardware requirements and long execution time. And also empirical analytical models, they usually are not enough general to model complete networks. So we propose the use of machine learning to model the delay of the network. So the advantage of machine learning are that machine learning is data-driven, and only with the data we can collect of a network, we can model it. And this model can be general if they are enough trained. So, but is this problem hard enough to use machine learning? We started studying a simple scenario with 2 nodes generating traffic to a third destination. And this is the function we have to model to study this use case. And this model is quite complex, only for 2 dimensions and nonlinear. So in real networks, the interaction among traffic in a node is much more complex and much more difficult to model. And also, if we are interested of dividing the traffic with flows, the number of interaction in a node is also increased, and this means that the complexity of the network is quite high. So this is the methodology we have followed in our experiments. We have simulated different networks using different topologies, size, traffic characteristics, and saturation. And we created different data sets, big data sets, containing the traffic as the input and the delay as the output. And we modeled them using artificial neural networks and to study the error achieved to predict the mean delay. So as I said, we have big data sets. The input feature is the pairwise traffic matrix, only the average traffic, and the delay is the average end-to-end delay of all pair of nodes. And we evaluate the result using the MSE error in the test set of the data set. So an important point is how to represent the traffic. In this paper, we only use the average bandwidth, but we can also include more characteristics of the traffic, such as the tuples or the number of ports or different characteristics of the traffic. So this is the first result to present. Here we model, these are 20 different neural network fittings using different traffic. This represents that the traffic is randomly generated among nodes between 0 and the rho max. Rho max is defined as the capacity of the links. So 1 means that the average traffic among nodes is 0.5. And we observe that when the traffic is high and the network is saturated, the error of the model increases. With 1 layer, the error increases a lot. With 2 layers, the fitting is better. And we also try with 3 layers, and the result is better, but the training time is high, and it's difficult to train the model. So this is why we didn't include the results. And the second experiment, we study different topologies and different number of nodes per topology. The ring topology, the traffic has to go through all nodes, so this ring easily saturated. So this is why the error is high when the number of nodes increases. And for the star and scale-free, the results are similar. And this randomness is due to that the scale-free topology is randomly generated. So in some cases, there may be a bottleneck in the topology, but the results, the accuracy is quite high. And finally, we study the effect of the number of neurons in the neural network. For small networks, for small computer networks, small artificial neural networks are enough. But when the network is big, we need a higher number of neurons. So as I said, the input features are the traffic matrix, so it's the square of the number of nodes. So for 5 nodes, there are 25 input features. So with 25 neurons is enough. And in the other case, with 15 nodes, there are 225 input features, so we need more neurons to represent to model the behavior of the network. So the contributions of this paper are this: that we we show that we can model the delay of computer network using artificial neural network models, and we tested using different traffic intensities, different topologies, and different network sizes. So the conclusion, as I said, is that we can model the delay of computer networks. The main source of error of the network of the model is the variance of the dataset, as the first keynote mentioned. And finally, we show that the most difficult to model is when we have high intensity in the network, since the function we want to model is more complex and more nonlinear. So what is the future work? First, how can we represent the topology and the configuration? The topology, we can use graph neural network as the previous paper presentation, but the configuration is a key point to representing the network to achieve the use case we presented. And finally, also how can we represent the real traffic of the internet in the network, and also computer network are becoming more complex, and we have to study if with more complex elements, forwarding elements, this can be learned as we show with simple forwarding elements. And that's all. Thank you for your attention.
Last chance to ask questions.
Hey, so you presented a few results with the mean squared error. What is error between what? Or how do you compute that?
Yeah, sure. For example, yeah, the error is, so each point of the graphic is a neural network model, a complete, and this represents the error between the test error, between the delay, so the aggregated the delay of the test error points. So this is the test error of the delay not used to train the network model. So the data set is, the input is the traffic and the output is the delay. We divide the data set, we have the test set, and this is the MSE of the test part of the data set, aggregated for all nodes.
Is the delay also randomly generated?
The traffic.
You said you randomly generate the traffic matrix, but you also randomly generate the delay?
Well, we simulate the delay according to the traffic matrix.
Okay, thank you.
And the packets are Poisson distributed exponential arrival time, or what?
We try different packet length distribution and different...
No, I mean the packet arrival process,
yeah.
Is a Poisson process or what?
In these experiments, this is Poisson process, but we also try other distributions.
And everything has to be stationary?
Yeah, exactly. So this is
some simple model.
A very interesting talk. And I have a question about the delay matrix. It has the same size as the traffic matrix?
Yeah, it's pairwise matrix.
It means the average delay between two network nodes. So there may be many different paths to connect two nodes. So what's the delay means here? Is the delay of the average delay of all the passes between these two nodes, or just one pass?
In this paper, we consider that the routing among nodes is fixed. So there is only one path between the source and the destination. We also try to add more flows inside one parent destination, so having two flows with two different paths, and it also works, but the price is more dimensionality of the data.
Okay. And my second question is that because you only input the traffic matrix, so if the topology changes, or if you got a new routing protocol, then you have to retrain the model.
Exactly. Each point is a different neural network model in the network. specific for the traffic characteristics and for the topology.
Okay, thank you.
Any other question?
Very nice talk. I have a question here. Can you two predict the delay with another given input traffic matrix with your method to predict the delay matrix?
Yeah. So your question is, hey, we can. So the model is specific for a topology, but it predicts the delay for any traffic matrix as an input.
Other questions? No? Okay, so let's thank the speaker again. And let me thank also all the previous speakers and keynote speakers as well. This concludes the workshop. Let me thank all of you for being here. I hope you got some interesting insight on research going on. This was a mostly work in progress papers, initial works. And today there will be the reception here in the hotel, if you're interested. Otherwise, we can go outside and look at the fireworks on the street with a lot of people. The reception will start at 8 here, and then you will not be almost allowed to leave before 10. That's because there will be so many people around, you will not be able to leave. So, up to you. Okay? So, thanks again.